Okay, so let's send this to myself and see if it works. So, in the interest of doing things when you think about them, my wife made a pot of soup last night, and I said, "I'm going to take this out and put it in the fridge." She's like, "No, no, no, it's too hot. You have to wait." And of course, what does that mean? If you have to wait, that means I forgot. So, yeah. Okay, there's the shack.
Ah, there you go.
Yeah, and it doesn't show the other side of it, which is the piles of antenna pieces and the workbench and the soldering station and the buckets of extra parts. And yeah, it's rustic and unheated, and it's like what 2.5 by 4 meters. It's a pretty good size, but it's full of stuff.
How can you stay there doing contest in the winter?
Uh-huh. I have a little heater, and
All right.
yeah, but you can see, like, on the left hand side, you see the antenna parts. There's a piece of a tripod and fiberglass and all kinds of all kinds of stuff. It's good and bad because my wife always knows where to find me. So no questions from yesterday? I know there's got to be some. I mean, I came up with some questions from yesterday. I got a handful of things that I wanted to cover. Okay.
Batteries,
Batteries,
picture of tuner
tuner
components.
components, what a meter does, shielding we're going to get to, the radio horizon, effects of vegetation. No questions. Okay.
I'm still trying to figure out why deciduous trees affect our radio signals on our ISP more than deciduous.
Or more than conifers, you mean? Which
Yeah,
one? What?
the
Well,
conifers affect more than deciduous.
really?
We with MIMO, yes, with MIMO we actually get less signal loss going through hardwoods than we do pine.
Yeah, but I don't think it's the wood. I think it's the branches and the leaves. And are you talking winter
What
or summer?
moisture content?
Yeah, I mean,
We're talking any time of the year. Of course, in winter we get better signal because the leaves are off. In fact, sometimes we will lose signal in the winter to a radio with MIMO um, because we can't get the reflective pathing
mm,
without the leaves.
and you
But
and you
it doesn't matter. Going through any kind of pine just kills signal like
really?
crazy.
And
Yes.
where do you live?
I'm in Michigan. We cover about 14 counties,
Okay.
and we're using 365 LTE for the most part, with some feed on some sub towers of 2.4
Okay. Well, to,
and some 5
well,
gigahertz, 6 gigahertz, and 80 gigahertz.
do you notice that on any particular band it's worse than others?
Um, 5 gigahertz won't penetrate pine at all, but a 5 gigahertz
Weird.
MIMO, we can get some non line of sight through hardwoods if
How
we've
about
got run room on both sides.
how about 2.4 gigs? Because that
2.4 gig, 2.4 gig will blow through stuff easier than the 5
interesting. All right, because we're talking, if we're talking wavelengths, let's see. So 3 gigs would be 10 centimeters. So,
Yeah, we
yeah,
use the CBRS.
That's kind of weird. I mean, I know that, you can get reflections off of leaves. Um,
Yes, and that's what
and
it
you
what
can
we're
you
definitely getting.
and you also get absorption due to leaves. So you get diffraction, reflection, and absorption.
Yes.
But, as far as honestly, I don't think the pine needles themselves would have much of an effect because they're so small compared to a radio wave.
But they're way denser.
But yeah, that's possible. A higher water content, maybe.
Yeah, that might be. I just know that when we're going through um, hardwood, it's way easier to get a signal on a non-line of sight than it is through our pine.
Let's see. Why does RF pass through deciduous? Better than conifer. Hmm. That's okay. My search didn't really help, but here's one. How much RF energy do trees and branches absorb? Trees absorb some, buildings, hills, structures. Yeah, that's a good question. You know, I it's all line of sight, but I wonder a little bit about the soil too. I mean, I know Michigan's got, depending on where you live, it's got a fair amount of iron in the soil.
Well, we're central, pretty much central Michigan.
So
Um,
like about here.
actually, over to the west side a little bit more.
Okay.
Um, if you go up north 30, 131 north, uh, we have network that runs as a center point out of Big Rapids. We go up as far north as Cadillac and then almost over to Baldwin and over to 66.
I can honestly say that I have no idea. So Rick, where are you exactly? And I don't
Are
know
you
if Rick,
talking to me or you?
Rick, no, Rick Howd.
In
Oh,
McMinnville, Elk Creek.
What? So what mill is it?
Elk Creek.
Okay. Like dimensional or engineered wood or paper or something.
Um, it's dimensional timbers up to 24 by 24 ish.
Whoa, that's a big piece of wood.
Yeah. Lots of hearts in those though.
Yeah, yeah. So yeah, I do mostly EWP. So I go into plywood, OSB, glue lams and stuff like that.
Oh, sure. Yeah,
So
we buy a little bit of glue lamb. Which mill are you with?
I'm actually with Willamette Valley Company. So we do chemicals and machinery and
Oh,
put them
okay.
in all over the place. Robotics, all kinds of neat stuff.
Nice. We're just putting in a new double head mill.
Okay. Yeah, so we I used to work with Sony down here in Eugene, and I note the comment you said about tablets versus phones and things like that. And so we at Sony we had automated guided vehicles running around the plant through the clean rooms and stuff, and they were running on 900 megahertz, and we were looking at bandwidth because they were, the network was kind of slow and a little congested. And so we had somebody come in and run a test on a 2.4 gigahertz radio system. And if you're familiar with 2.4 gigahertz, you will note that there is something pretty close to 2.4 gigahertz that we use every day. Anyone know what that is?
Wi-Fi.
No, besides that, we know
Oh.
Wi-Fi.
Microwave.
Microwave oven, yeah. So a microwave oven operates at about 2.45 gigahertz. And depending on how clean the microwave transmitter is, it's a kilowatt. Um, Even a little bit of energy, as we saw yesterday, can get in and really, trash the communication. So if you ever notice that you lose your Wi-Fi signal when somebody runs the microwave, you might have a little bit of microwave leakage getting out. It doesn't take much. I mean, nanowatts, picowatts, getting to your receiver is enough to, as we saw yesterday, do some, do some harm to the receiver's ability to hear anything.
So
Well,
somebody in the office would heat a cup of coffee and robots around the plant would stop.
well, no, actually, that was fine, except that we also had in that same facility, we had 18 curing ovens for ink because we were doing all the printing on our compact discs. And so those were ultraviolet lamps, but they were an ultraviolet tube inside a microwave. So the microwave basically would generate a high voltage and it would fire the ultraviolet lamp. And that light would then pass through a grid, which would in theory keep the microwaves in, but each of those was a kilowatt times 18. So we had 18,000 watts of microwave ovens in that facility. So anytime any of the machines and anytime any of the automated guided vehicles got anywhere near that part of the factory, they would just stop running. We call that the end of the test. Like, yeah, this isn't going to work. I went so far as to go get a spectrum analyzer for a few days, and like, yeah, this isn't going to work. Questions before we get going? Today's not as technical a day as yesterday.
I do have one little stupid question.
Okay, no such thing. Go for it.
I've been studying my book ahead of time. Does it matter how long your coaxial cable is going to your antenna back to your base?
Yes, we're going to cover that in about 10 minutes, I hope.
Okay, good. All right.
There's a good reason for that too.
Okay.
And use LMR if you can.
I'm sorry?
Well, it depends on the frequency you're using.
Oh.
So we're going to get to that specifically for that reason. And let's say it involves, whoops.
Isn't there some form of loss depending on the length of a cable? It's the same thing with data cables or network cables. You depending on your length, they bounce off the walls and you'll lose some form of data.
Exactly right. Okay.
Yeah. I did
All
read.
right. It's 9 o'clock. Let's get started. All right.
Good morning,
So,
everyone.
Good morning. So, all right, a couple of things I wanted to point out from yesterday is that one thing that we didn't cover exactly was what a meter does. Okay, so a meter is a length of cable, or a physical length. A meter is actually also used to display something. So we can have something that is a watt meter or a voltmeter or any other kind of meter, and it's just a way of displaying something in a numerical value. The radio horizon was one other thing that we didn't quite get to. We mentioned the fact that this is the Earth and the Earth is curved. Well, what ends up happening is that if we have, let's say, a sharp point, and we aim a signal any wavelength at this, that can either be a single thing or it could be a slit, doesn't really matter. What ends up happening is that when the wave gets to that point, the wave tends to diffract and spray in all different directions, and that's called knife edge diffraction. we we don't get the exact same thing with regard to the Earth's surface, but what ends up happening is that proportional to the wavelength that we're doing, let's say light looks like this and radio waves look like this, right? So we have a very, 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 very short wave. So if you look at the curvature of the Earth per wavelength, light waves basically will travel a straight line. Radio waves are so long that they actually tend to look over the horizon a little bit. So because the wavelength is so long, the Earth doesn't look quite as curved if you're sitting on a radio wave. So it tends to hug the surface of the Earth a little bit. So the visible horizon might be here, and the radio horizon might be there. It's still not going to go very far, but it's going to go a little bit further. And actually, when radio waves hug the surface of the Earth, we actually call that ground wave. We were just talking for a moment about vegetation, and microwave oven operates at 2.405 gigahertz. All right, everybody, what does gigahertz mean?
Million?
Billion.
Million.
Right? Billion hertz, 2.4 billion hertz. Well, it turns out that this is a very convenient frequency to use because we have a molecule that looks like this, kind of a little bit like Mickey Mouse. Any idea what that is? These are hydrogens,
Water.
and that's an oxygen. That would be water, yeah. Well, the way that the water molecule is laid out is that the angle is not, it's not axial. They're actually off at an angle to each other with the hydrogens, and that's because of the way the bonding is done internally, et cetera, electron pairs. But what really is important about this is that the water molecule, because of how it is laid out, how it is constructed, has a resonant frequency of about 2.405 gigahertz, which means that if you have radio frequency energy at 2.405 gigahertz or thereabouts, this will actually cause the molecule to bounce back and forth, cause it to transfer its energy to it. That'll cause it to move. Motion, yeah, motion has another name. Motion is heat, it's temperature. So when you stick water inside a cavity that contains large amounts of energy at 2.4 gigahertz, you heat up your water. Microwave oven. Discovered completely by accident by, I believe, and made commercial by Amana with something called the radar range. This is actually really important also because let's say that you have a transmitter here, and we're going to make a little Yagi antenna. That's the driven element. This is a dipole antenna. Main direction of transmission is this way. Well, so now what we're going to do is we're going to put a tree over here. And trees contain leaves, and leaves and wood contain lots of water. So you aim your signal at the tree. In the winter, it's going to hit mostly branches and no leaves. But during the summer, you're going to find that the tree has a lot of these things called leaves, which have lots of water. They're flat. They have flat surfaces. Those, depending on the frequency you're using, will tend to catch the vegetation will reflect waves. And also, depending on the frequency you're using, it can actually heat the leaves. So if you heat up the leaves, what does that mean for your signal coming out?
Distortion.
Or it goes away. Yeah. So has anybody ever noticed if you have like let's say satellite radio and it's raining really hard, or you're trying to pick it up while you're driving and there's a whole bunch of trees nearby between you and the satellite that you're listening to? What will happen is, depending on the frequency that it's operating on, the signal will get distorted or absorbed by the vegetation.
Yeah.
Or by the precipitation. So microwave microwave frequencies, when you get into rain, those tend to get distorted and absorbed. So you'll have a weaker signal. All right, let's see. There was one other thing I wanted to talk about, which was practical use. Now that we've covered impedance, does everybody remember what impedance was?
Resistance.
Well, it's resistance, but not quite. Resistance
Well,
is R, measured in ohms, and it's something's ability to resist the flow of DC. Reactance is the resistance of flow specifically to AC. And then impedance is equal to R plus IX. This is kind of something's resistance of flow to everything, but we're going to go with AC. Essentially, the resistance becomes a component of it. The reactance is another component, but impedance typically we're going to say is something's resistance of flow to AC current. So when we're talking about that, what we can do here is we have a few different ways to transform or convert resistances and impedances. Does everybody remember what this is called?
transformer.
Transformers.
That's a transformer, right? So that can be used to transform voltages and currents and also impedances and resistances. So that's a transformer. That's one way to do it. We also have another tricky way to do this because we have, okay, this is like a little quiz from yesterday. What's that thing called?
Resistor.
That's a resistor. And what's this thing called? Another resistor.
Another
resistor. Okay, so what is the total resistance in this case? Resistance 1.
R1 plus
R2.
R2.
Two.
Yep. Okay, so in series, those resistances add. Now, I could also change that. I could make these Z1 and Z2, and they still add. So it'd be Z1 plus Z2. So if I were to take a resistor and replace it with a capacitor, it still has a Z. I could take this one and replace it with an inductor, and it still has a Z, and they add together. You might remember that this has a negative reactance, and this one has a positive reactance, and you can make them so that they are equal to each other and opposite, and the Z minus Z is 0, in which case this becomes a short circuit. So that is how that is one way to look at something called resonance, the same way that same way a flute resonates when you blow into it, or a Coke bottle resonates when you blow into it. If you set your capacitor and inductor equal to each other, you get to resonance, and that is a natural vibrating frequency of the circuit. It basically transfers energy back to from electric field energy to magnetic field energy. And those two devices basically transfer it back and forth. And in doing so, they make the circuit look like it's not even there. They just transfer it back and forth and back and forth and back and forth because they're both energy storage devices. Now, one interesting thing about this is that we can draw another circuit that uses these things, which is actually very, very useful. Okay, so this thing up here, this is an antenna. From here on today, I'm going to be using that schematic symbol a lot. That's an antenna. Okay, so I'm going to put elements number 1, 2, and 3. Okay, so what is element 1?
Capacitor.
Yep. Okay, element 3
Capacitor.
and element 2.
Inductor.
Inductor. Okay. Now I'm going to do this to all 3 of them.
Variable.
And that makes them variable. Okay.
Antenna
So
tuner.
So an antenna is kind of a weird thing, right? Because you push power into it, and ideally, what happens to that power?
It leaves.
Where does it go?
Where you're sending it.
That's right. It goes off into space. So if you think of it as a resistor like this, if you think of it as a resistor, where does that power go when you put power into it? Heat. Okay. But now here's the question. From the outside world, if I just look at this thing and I put power into it and I just don't see it coming back, do I have any idea where it went?
No.
No.
I don't. This, for an antenna that we're going to draw here, is called radiation resistance. It's not actually resistance. It is the equivalent resistance that something would have if it were a resistor and I was putting energy into it and I never saw that energy come back. So that's essentially it's a calculated thing, but it helps to understand why, for instance, a dipole antenna, for instance, has, like, if I hook it up like this, if I feed it right here, it has an impedance, which is mostly resistive, of 72 ohms. It's like, wait, how can two pieces of wire hanging out in space have an impedance of 72 ohms, mostly resistive? That doesn't make any sense, right? It's not a resistor. But what it's basically saying is that equivalently, if I were to treat this thing as a black box and I run power up to it and it disappears, it is acting as though it were a 72 ohm resistor. But instead of turning it into heat, it's the energy required to launch signals off into space. And that's known as radiation resistance. Now, we're going to get into feed lines very, very soon. But what's important to note is that as I erase this right here, we're going to say that we have some antenna or a dipole. We're going to say that we have a dipole, which is a half wavelength antenna. But we're going to operate it on a frequency which is away from its resonant frequency, in which case it is not a half wavelength anymore. It is something else because we changed the frequency. If we were to draw waves on this, it would now look like this. That's not a half wave anymore, is it? That's a whole bunch of half waves. It might work, but it's not the same antenna anymore because we left the antenna physically at the same length, but we changed the wavelength that we're drawing on it. We changed its operating frequency. Well, is this antenna still 72 ohms?
Yes.
Probably not, honestly, because remember, it's an equivalent of how we're launching signals up into space. And that's not a half wave dipole anymore. So it might be 72 ohms and it might not. We don't really know what it is at that point unless we go and model it or test it. So we can do with this antenna here. Let's say
Scott,
yeah.
can you tell us why we don't know? I mean, it's still 72 ohms. It's still that length.
Is it?
I don't know.
Exactly. And the problem is you don't really know. It might be, but it might not be. Because what is impedance equal to? E equals I times Z, right? So Z is equal to E divided by I. If instead of having a half-wave antenna, which looks like this, and the voltage is right here, well, okay, we're not we're not looking at that anymore. We're looking at an antenna where the current might look like this, 0 at the ends. Well, and the voltage might look like this.
Got it.
We don't know what we're looking at anymore. So it is now something different. And we don't know exactly what it is. This is actually a very common problem for anyone who wants to use an antenna for two different frequencies, or every different frequency that they can think of. I have two antennas up in my trees, and I use those two antennas. And that's it for all the different frequencies I can think of. So that means I don't really know what my impedance is. So Z is equal to question mark. Okay, but now what can I do with this capacitor? Z is equal to -1 over, or negative I over 2 pi FC. For this one, Z is equal to negative I over 2 pi F1. And for this, it's 2 pi FL2. And I can change all of those. And I can tune them because they're all variable. Now, what I also have is I can show this as being ground because it is ground. What is the definition of ground, everybody? Remember what ground is?
Zero voltage?
Zero reference.
Zero reference.
It's our zero reference point. Okay, which means that this is at 0 volts, which means any signal that goes down into ground is never seen again. Does everyone agree with that?
Mm-hmm.
Yes.
Okay. How about a signal that goes out into the world? Is that ever seen again by you?
Could bounce off something.
Yeah, but as far as you transmitting it, it's never seen again.
No.
Yeah. I need you to plug it in because I'm using it. Hold on a second. Hold on. My daughter is W7HR. I need it. You need to find another charger. There you go. Take it. Take it. Sorry. Apparently I stole her charger. So say hi, Hannah.
Hi, Hannah.
She's got her extra class license. So
Wow.
okay. Yeah. Okay. So if a signal that goes to ground never shows up again, we have stuff going out to the antenna. This can be viewed as, in theory, going to ground because it's never seen again. So this is like an RF ground. But anyway, what that really means is that this one, number 3, this capacitor, and the antenna, number 4, are actually viewed as being in series. Because they're in series, it's ZC3 plus Z antenna. And then number 2, because this is going up to ground, this is going down to ground, and that's in parallel with ZL2, which is then in series with number 1. It actually gets kind of complicated, but what it really means is that this circuit right here, if you have an impedance here, by changing these different values of impedance because they're tunable, that can make the input impedance right here look like a whole bunch of different things. Essentially, this is a magic box which tunes the entire circuit so that it can behave and look like something totally different. It doesn't fix anything, but it makes your transmitter very happy. Most equipment has a characteristic impedance of 50 ohms. That is what we like to see. That's how maximum power transfer occurs from your equipment to your antenna system. Most coaxial cable has a characteristic impedance of 50 ohms. It doesn't mean it's a 50 ohm resistor. It just means that it looks like if you put a 50 ohm resistor on the other end, the signal goes out and goes into the resistor and never comes back. There's no reflections of any kind. So this is a magic box. And where do we find this magic box? We find this magic box all over the place. And I'm going to show you where we find the magic box. Here we go. There's one version. I want to see the internals. There we go. It's not a very good photo. There, that's a better photo. And okay, can everybody see this? Can everyone see that photo? Okay, so what do you have? What do you have on the left side? What is that thing up on the upper left? That's a big coil. Coil has coil's another name for
Inductor.
Mm-hmm. How about on the right side, up toward the top?
Variable capacitor.
Those are multi-plate variable capacitors, which you tune from the front panel by basically meshing more or less of the plates with each other. That changes the capacitance. How about down here at the bottom, that big long black thing?
Fuse.
No, that's a 50 ohm non-inductive wire wound resistor that's capable of dissipating 300 watts. That's for doing that's for doing off-air tests of your equipment. And how about this little thing down at the bottom?
No idea.
Anyone?
Oscillator?
Ferrite.
Yeah, it's a ferrite. That's a ferrite core. That is a toroidal core that has been wrapped with wire multiple times. Any idea what that would be used for?
Choke.
Actually, not in this case.
Inductor.
Nope. It's an impedance matching device, and it's a piece of metal, or it's basically metallic powder that's been baked into a shape, and wire is wrapped around it, and then another wire is wrapped around it.
Transformer.
That is a transformer. So that looks like that. That is a transformer, and that is an impedance matching transformer. And in fact, that's also known as a balun, which is a balanced to unbalanced transformer. So it takes coaxial cable, because your currents are not the same on the outside and the inside, and matches that to two parallel wires. This is typically known as ladder line, where you just basically have two equal wires that are encased in plastic and spaced a certain distance apart. So that's known as a balanced, there's the balanced part, to unbalanced, which is coaxial cable. It allows you to change the impedance and also change from balanced to unbalanced wire. Cool stuff. This is used all over the place. All right. Any questions before we go on?
On antennas?
We're getting to more antennas now.
Okay, I'll wait. We'll see.
Okay. All right. So we're getting to more antennas, and the more antennas we're talking about now are how to calculate the length of an antenna. Okay. So does everybody remember the circle that we drew yesterday? That looks like this. Everybody remember that circle? Okay.
Yeah.
So what we're going to do is we're going to start with an antenna, which is a half wavelength at 146 megahertz. All right. So We know that this 300 implies that we're working with megahertz because we took away 6 zeros there. So our frequency is 146 megahertz, and our wavelength is our length of our antenna is going to be a half wave. So if it's a half wave, what does that mean? That the first thing we have to calculate is?
Yeah, the length of the.
We have to calculate a full wave, right? And since we don't know this one, wavelength is equal to 300 divided by 146. Everyone good so far?
Yeah.
And that's a physical spacing, physical distance, 2.05 meters. Okay, how long did we say this antenna is going to be?
Yeah.
Half of a wavelength. So a half wavelength is
1.025
1.025 meters. Okay. All right. So now we say, okay, well, if a half wavelength is 1.025 meters, how long do we make our antenna? And if it's a half wave antenna?
1.025.
Except that's actually a little bit too long. The rule of thumb is that because wire has inductance and because things couple with everything around them, the good rule of thumb is we take 95% of this. Whatever that length was, we take about 95%. And that's a good starting point. And this is where the theory, which is this being the theory, does not quite equal the practice. The practice says that actually what we're going to end up with is 95% of 1.025. So that's about 0.97 meters. And we can calculate this to inches, 39.36 inches per meter. And what do we get? About 38 inches. So if we were making a half wave dipole for this frequency, 146 megahertz, it would be about 38 inches long. And that's how you make an antenna. So what would happen if we wanted to, if we put our antenna, which we just built, and we were able to sweep the frequency and watch how the antenna was behaving, and we found that its resonance looked like this. And we found this nice dip right here, which implies that it's good. And we found this at 144 megahertz. What does that mean for our antenna?
It's resonant at 144 megahertz.
Right, but where did we want it to be?
146.
Okay, so what does that mean we did?
Cut it too short.
Anyone else?
Too long.
We cut it too long. It's resonating at too low a pitch, too low a frequency. So we made it too long. How about if we made that same antenna and we found that it was resonating at 148 megahertz? What does that mean?
We screwed up.
We made it too short. Okay. Which one would you rather do?
I'd rather be too long.
Yes, because
I can cut
You
it.
can always
cut it.
Trim. Yeah, you can always trim an antenna.
You can always trim it. Yeah, it's a lot harder to add it back. And that's why you have so many, as I saw, so many spare broken antenna pieces everywhere. If you made it too short, you start again.
Question.
Uh-huh.
You keep talking about how making dipoles. Why would we not worry about calculating isotropic radiators, which are more efficient?
An isotropic radiator? Wait, a what?
Isotropic radiator.
Because there's no such thing.
Uh,
You cannot build an isotropic antenna. It doesn't exist.
if it's in theory, it can be built.
Yeah, but in practice, it's impossible. So for everyone who's curious, and I'm sure you all are, a dipole is the fundamental antenna, right? And that has a pattern which is, as they say, broadside to the wire. So up, down, forward, and backward, and nothing off the ends. That's a dipole antenna. An isotropic radiator is a point source that exists in space, which sends equal signals in all directions. Unfortunately, this cannot be built and does not exist. The dipole has a gain of 2.05 dBi. You will see this, sorry, 2.15 dBi. You will see this quoted a lot of times. This is actually a very important distinction because a dipole is the fundamental antenna that we can build. And it is actually 2 decibels roughly better than an isotropic radiator, which is why there's that letter I. An isotropic radiator is a theoretical antenna, which is a monopole, which radiates equally in all directions, and it cannot physically be built. You can get things that are closer to isotropic in gain, but which antenna has more gain?
A dipole.
A dipole, and by about 2 dB. So, yeah,
In one
because
direction.
right, in one particular direction. In other words, you give up that you give up the ability to transmit in all directions, and you gain a little bit back in one direction. That's why it works a little better, because power in has to equal power out.
Scott, quick question. From your previous drawing there, you had 300 divided by 146, so 2.5 meters. Then we take 95% of that, which represent 0.97 meters. Then you come up with 39.36 meter. Where's that number coming from?
Well, okay, so you're so that wasn't meters, that was inches. Because in the United States, we're still locked into doing things in inches and feet.
The light just came on. Thanks.
Yeah.
Another question?
Yeah.
So that length, the 95% length that you're cutting at, if you're working with a dipole, you're I'm assuming, doesn't necessarily have to be this way, I suppose, but it's center fed. So that's the entire length?
That's the entire length.
How do you account for the center feed component and any
Yes.
separation, all that stuff?
Yeah, but make it a little longer. Try it, trim it, try it,
Okay.
trim it, try it, trim it.
Okay.
It's always safer to do that.
What is the purpose of that device with the inductors and capacitors?
Well, so what that does is, let me do another share. Okay, so let's say that you have a dipole, and this is a half-wave dipole, and and it's center fed. What's the impedance going to be at the center if it's a resonant dipole? Which means that it's going to be 72 ohms. Right. 72 ohms, purely resistive. What happens if you now change it so that you're not operating it at its resonant frequency? You're operating it at a frequency where it looks like this. That's the current curve, and it's no longer resonant. So the impedance is R plus IX. That's what it is. I mean, the problem is now your impedance is R plus IX, and you don't know what this value is. So you want to hook this up to a piece of equipment down here that has cable coming out of it and maximum power transfer, because most cable is going to be 50 ohms impedance. This circuit is designed to transfer power efficiently into an impedance of 50 ohms. What is the impedance of the antenna?
72.
No, it's not.
No?
It would be, but what is it now?
You don't know.
Don't know.
Oh, I don't know. Yeah, no idea. So let's say I connect this cable up to here like this. And I have 50 ohm cable. So I have 50 ohm transmitter, 50 ohm cable going up to a match, which is this is a chance to bring in something called standing wave ratio. Standing wave ratio is an impedance calculation that shows how well matched one side of the barrier is to the other side. A perfect match is a 1-to-1 standing wave ratio. If you have something that is not perfect, the same on both sides, you will not have a 1-to-1 standing wave ratio. So let's say that you calculate what this is, and it's actually 200 ohms. Has anyone ever taken a piece of rope or like a garden hose and tried to uncoil it by whipping it? And what you see is you'll create like this disturbance and it will propagate down the line.
Yeah.
Right? Okay. If you were to take that and instead do this with it and take a piece of rope and hook it up to a doorknob and you whip it, what will happen to it when it gets to this point?
Right now,
comes back.
It'll rattle the door unless the door is really, really tight. But what'll happen is it'll either come back above or below, and that signal and that wave that you created, that energy will bounce back, right? Well, if you're looking at this as an antenna, ideally, what do you want to happen to all the energy you put into the antenna?
Leave.
To go out.
You want it to never come back. But what happens when you build this antenna system that we just built with 50 ohms here and 200 ohms up here? That is a mismatch. That is like tying your cable. That is like tying your rope to a door. What happens is that you get some of the energy going out and a good amount of it coming back. That then travels down here, and where does it end up? Has to go somewhere. Where does it go?
Into your radio.
Back into your transmitter.
Grounded.
Right, back into your transmitter. So let's say that your transmitter is built with circuits that use transistors, and it has a maximum voltage of 32 volts. And in order to generate the power that's going out, it is operating at 24 volts AC. And the reflected signal is 16 volts AC. And it comes back in here. If you are unlucky enough for that to actually combine and they add together, what is 16 plus 24?
40.
That's 40 volts. What will happen to your beautiful 32 volt transistors?
Oh, the magic smoke will come out.
You let out, yes, you let out the magic smoke. You let out the magic smoke.
Magic smoke.
Yep, you let out the magic smoke. So what happens is that this device, which you will put in here as a black box right here, is an impedance matching network that looks like this. And this can take multiple different forms. This is known as a T network. You can also make it in this shape. That's known as a pi network because it looks like the Greek letter pi. Essentially, what this allows you to do is hook up your transmitter here, which is looking for 50 ohms. And here's your antenna, which has an impedance of something. And here's ZC2, ZC1, ZL, and put things by adjusting them in series and in parallel and changing what this transmitter sees. So you might still have 50 ohm cable right here. The antenna might still be 200 ohms. It might still be something else. You don't really know. When you get to this point, you still have a mismatch where power is getting up there, it's bouncing back and forth, but then it gets to this magic box, which is known as a transmatch or an impedance matching circuit, antenna tuner, it's sometimes called. And what happens is the signal, before it gets back to your transmitter, will get back to this device, reflect, and go back out. So you might still have signals going back up and down and up and down and up and down many, many times, depending on how bad your match is. But you will still be able to deliver full power into the antenna, at least in theory, and it won't destroy your transmitter.
Question.
Yes.
What about power loss?
Okay. Well, okay. So let's say that we now have this.
My transmitter has a 50 watts out But
Uh-huh.
after the antenna tuner, how much
Yeah.
watt
Well,
effectively do I have?
we could calculate this. Okay. So let's take a look at this system that we've now built. Okay. So this standing wave ratio, we take the bigger impedance and divide it by the smaller one. 200 divided by 50. What's that?
4.
4. That is a 4-to-1 SWR, known as a standing wave ratio. It's a measure of how big the signals coming back are compared to the ones going out. This is a very poor SWR. That is a mismatch. If I had 100 ohms, that would be a 2-to-1 SWR. Similarly, if I had 25 ohms, well, it's not 25 divided by 50. It's always the bigger one divided by the smaller one. That would also be 2-to-1. These are kind of okay. They're passable. 4-to-1 is where you start to get into really big problems. And in fact, what will happen is if your transmitter experiences this, there's protection circuitry in your transmitter that will typically reduce the power output so that that doesn't fry the transistors in most circuits today. Okay, so we now have this. All right. So what happens up here? We have this magic box. And so here's we call it an antenna tuner or a transmatch or any number of different things. It's an impedance matching device, which makes the outside world look like 50 ohms to the transmitter. So is the transmitter happy? Yes or no?
Yes.
Yes. Okay. Now the power, it goes somewhere. So it's going to come up this way. What happens when it hits this barrier? Some of it goes out and some of it
It's reflected.
gets reflected. It gets back to this point. And what happens when it gets to this point? It gets reflected back this way. It goes out, some of it goes out, and some of it bounces back. It gets back here, bounces back up to here. Some of it goes out, some of it comes back. Okay, what do you see going on here?
Oscillation.
Well, it's not oscillation. I mean, it is in a way. It's ringing. It's bouncing up and down, back and forth. So so if you were to take a look at this, the worse the match is, the more power comes reflected back. We were getting to this with coax and transmission lines. Coaxial cable is the most common transmission line. Coaxial cable is measured in loss in decibels per 100 feet. And it's frequency dependent. And it's also, as you see, length dependent. So if you have really good cable, you won't have that much loss. If you have really crappy cable, you'll have a lot of loss. Every time your signal has to pass through that cable, what does it do to the cable?
Gets warm.
It gets warm. It dissipates some of its energy depending on the quality of the cable, which means that if I have 100 watts going out and I have a poor match, 4-to-1 SWR, I can make it work. But how much power actually gets out into the real world? Maybe 25 watts. Maybe 25 watts. And how much power gets burned up in heat?
Order.
75 watts.
75.
Has to show up somewhere. So basically, of the 100 watts of RF energy that I'm putting out, I actually get 25 watts out. And depending on how good or bad my cable is, this could actually be, if it's really lossy cable, this could be 10 watts. Then where does the other 90 watts go?
Heat.
Yeah. Heat. So not an efficient system.
So which is the best way to make the system, how to say, efficient?
You have a
without an antenna tuner.
No, well, you pick an antenna that has an impedance that is about 50 ohms. And that is why when we build an antenna, let's say if we build an antenna that is designed for a single band, so here's a quarter wave vertical. This is what I have up on the roof of my house for 2 meters. It's 19 inches long. These are about 19 inches long. That's my ground plane. This has an impedance right here, a feed point impedance of 50 ohms. Well, if I hook up coaxial cable to it, that's 50 ohm coaxial cable. Hook this up to my transmitter. That's looking for a 50 ohm impedance. Guess what?
1-to-1.
So you
1-to-1 perfect SWR.
so you are not using an antenna tuner.
There's no antenna tuner. I use this on the 2-meter band because it's a simple antenna. It's easy to build. It's not very big. It's really cheap. And because it operates from 144 to 148 megahertz, or Giovanni, in your case, 144 to 146.
Yep.
144 to 148, I get a pretty close to 1-to-1 match across the entire band. I don't need a tuner. If you, let's say, have an antenna that looks like this, it's a half wave long. It's a half wave on one particular frequency, right? Let's say I now operate it on a frequency, change frequency so that it's not a half wave long anymore. It actually looks like this. What's happening now is that we're feeding this at a low current and high voltage. That has a very high impedance. This might be 1800 ohms. Well, if I have 50 ohm cable feeding into this, I have a terribly matched antenna. So I can either replace this with something else, or the other thing that I can do is I can take these elements and I can make them half as long. There are antennas that are actually tunable for doing this. There's also something called loading.
Right.
So here's a vertical antenna. And this might be 8 feet long. If I want to extend this antenna, I can do loading and put a coil on it. This length electrically is included in the length of the antenna. So this actually might be 17 feet electrically, but only 11 feet mechanically. And this is known as loading. Now, notice that this is a coil, right?
Can
It's
you
an
make the coil as long as you want? So I mean, can you?
You can, but how much radiating does that coil do? It does very little. And here's the other thing. If I have, let's say that this is 17 feet long and it's actually resonant at, that would be a quarter wave at 20 meters. Here's my current distribution. And my current distribution goes like this. But all this stuff is basically wasted. It doesn't radiate. It would be better if I could make this antenna so that it looked like this. And put my coil up top. No reason I can't do that. Except now I have to deal with all that weight at the end of an antenna. Because then my current distribution is very low here where I'm wasting it, and it gets bigger here. End loading versus center loading or base loading.
But wouldn't you want the coil low? Wouldn't you want it not at the top because you want higher line of sight?
No, it won't make any difference. The way to gain line of sight is put the whole thing up on a building or a tower or something.
Right. Okay.
You want to get it up off the ground.
A little bit wouldn't make a difference. Okay.
That's why people do mountain topping. That's why people buy property in high places. That's why I live on a hill. That was quite accidental, but it worked out quite well. So
true.
Okay, so we inadvertently moved into cables and stuff like that. So thank you for causing me to segue into that.
Does it matter what your antenna is mounted on as long as it's grounded out properly?
Well, actually, when you say grounded, ground is a challenging thing because ground can be very, very lossy. If your antenna is heating the ground, it is causing energy to be dissipated and wasting its efficiency. So, ideally your antenna is isolated from ground, unless it's specifically a ground mounted antenna, which is a different design. And if you do that, it basically requires currents to be able to not dissipate as heat in the ground, which is why if somebody does that, they use the roof of a car or a metal roof on a building. That works okay if it's one big piece. Or for instance, if you're going to do a true ground mounted vertical antenna, you might bury 120 radials on your property. So
a specific number.
Well, it could be 64. It could be there's a point at which there's not much improvement, but if it's truly ground mounted, then it does make a difference. So, okay, let's see. We did that. We did that. We did that. We did that. Okay, so notice I'm going over to the book because we're getting closer to operating with the book now.
Can I ask a question about dipole?
Sure.
So I have a dipole center fed, well, actually it's slightly off center fed dipole antenna for a variety of frequencies. And, ideally it would be completely perpendicular to the surface of the earth, but in the practical applications, it's basically higher on both ends and it dips slightly to where the center feed is. How significant a problem is that how far off of straight?
How high up is it? How high up is the feed?
It's about 30 feet,
You're
although
fine.
I do have a metal roof, so it's maybe about 20 feet off the metal roof.
Yeah. Okay. So basically, you typically, ideally, you want to be a half wavelength above the ground.
Okay.
But what does that mean if it's a half wavelength above the ground and you use it for different frequencies? You're not changing how high it is, right?
Right.
So depending on the
different heights above the ground, depending upon where along that dipole
it's different, right? And it's different fractions of a wavelength depending on the frequency that you're using. So, yeah, and that's why we do something called antenna modeling. We use software called 4NEC2 or EasyNEC, or basically it's whoa, I can't remember what it's called. Numeric electromagnetic code, I think, was developed in the early 70s and originally run on mainframes, which allowed people to electrically and numerically model antennas before they built them to see what the patterns would look like. And it's free. I would strongly recommend. It typically takes a little while to get into it and understand what's going on. But if you really want to know what your antenna is doing, I would strongly recommend going through that process.
Hey, Scott, what was
the URL or was the?
I have a question when you get a second.
Okay. Well, you can use either 4NEC2, 4NEC2, or EasyNEC.
Thank you.
Easy NEC. They're both free and they work really well. And they have way more capability than they did back in the early 70s. Go ahead, Steve.
Well, you made comment of you typically want to be about a halfway above the ground.
Ideally.
What happens, and the reason I ask this is I have a 120-foot tower.
Lucky.
Well, luckily, I have a company that we supply internet. It's a feed tower out to some of our other towers. And I was planning on putting it up on top of that.
Mm-hmm. Oh, it's okay to be higher.
Okay.
Yeah. No, don't get me wrong. It's definitely okay to be higher. The higher up you get,
myself by going on the top of that.
No. Everybody would like that. Because the higher up you get, the closer you get to being an antenna in free space. And an antenna in free space optimizes everything. So there, your calculations of what your pattern looks like are really close to reality, which is really nice. So
Okay, so
no,
yeah, I was just starting to
everybody
worry when you said you
no.
wanted to be a half wave
At
above the
least
ground, and I'm
at
like,
least a half wave.
oh, okay,
At least a half wave. And
okay,
many people can't do that. And the closer it gets to the ground, the more vertical the pattern becomes, and that becomes something called a sky warmer. It's NVIS, which is near vertical incident skywave. It's really typically good for like 80 meters, 40 meters, working people very close in. But if you happen to be interested in working long distances, if most of your signal is going up toward the sky, it's not going to be talking to people far away.
right,
So,
right. So okay, well, I'm a little more at ease now then.
okay. All right. So now what we're going to talk about
Can I
is
break in a
speed
minute?
lines. Yep, go ahead.
I'm going to ask that question now. I happen to see, I think it was a Marine Corps thing that was given to the people that are in Black Ops or whatever, and it was how to build an antenna from nothing in the jungle or wherever.
Mhm.
And they talked about using coax, and all they did was take two pieces of wire and twist them together.
Yep, that works.
So
Yeah.
so just a twisted pair will work.
There's something very important to remember. Here we go. That is your mantra. Any piece of wire is an antenna, whether you want it to be or not. This is actually why it is very important to think about this. Let's say that you have a, let's say that you have a wire that is running this way. And on one end, you have a microphone. And on the other hand, you have your transceiver. And this is connected by a piece of wire. And you are transmitting with your antenna. And your energy is coming out in all directions. Is some of your energy coming back into your station?
Yes.
Sure. Okay. What is this piece of wire connecting your microphone to your transceiver?
Antenna.
It's an antenna, right? Okay. Have you planned for that to function as an antenna? I don't think so, right? But that's going to pick up RF energy because it's an antenna. It's a piece of wire. Any piece of wire is an antenna, which means that some of your transmitted energy is going to get back into your transceiver on what should be only carrying what kind of signals?
Microphone.
Audio, right? That will distort the heck out of it. So what we do in that case is we can put a toroidal core and choke it, or we can also do this. Does anybody do like audio? Does anyone do audio for like sound systems? Music, stuff like that?
Yeah, they use coax.
Yep.
Shielded cable. Why do we use shielded cable? Because it's shielded. The environment inside is protected from the outside because every piece of wire is an antenna. The energy that's being picked up is going to be carried on the outside, which is going to go to the case, which goes to ground. So by shielding this, what you've done is you've protected the wire inside from what's happening outside. That's why we have shielded cable. The other thing to do is if you do actually think, okay, we're getting some of this signal on, where did it go? Hold on. Zoom workplace quit unexpectedly. Can everyone still see that somehow?
You see it, but not see it in movement.
Yeah, I can see it.
Yeah, that's weird. Where'd it go? All right. I got to make sure it comes back. Okay. So while that's happening, let me go back to. Sorry, that got wiped out somehow.
Scott,
Yeah.
we're a little past it now, but how does all of the like impedance matching for antennas relate to like small handhelds?
Well, the thing is, how many different frequencies are you going to be going to be using a handheld radio on?
I mean, not too many, I think.
Exactly. So what you can do in that case is, can you still hear me okay? Okay, good. What happens in that case is that your antenna is now designed for a certain range of frequencies, and you're not going to use it anywhere else. So because of that, you don't need to have any kind of matching network.
So there's not like a small
No, I mean you can build one. Now there might be some kind of transformer needed if you're going to decide that you want to feed something larger. You know, some kind of antenna that you designed yourself that you want to have, you want to have operating on different frequencies. You may end up doing that. But like, let's say I have a handheld radio and it has an antenna that looks like this sticking up off of it. That antenna is going to be specifically designed to operate on the frequency of the radio. So if the radio is operating at 144 and 430 megahertz, well, it turns out that 144 megahertz, that's going to be 19 inches long, and this is going to be about 7 inches long. Well, it turns out that this 430 is roughly the third harmonic of 144. Third harmonic being an integer multiple, which means that that antenna is going to be a quarter wavelength long on this frequency and 3/4 wavelengths long on this frequency. And actually the same antenna for the most part works for both. Another cool thing. And if I were to draw a dipole, that would be this on one frequency and this on the other frequency, which is maybe not exactly 50 ohms, but it'll be close enough. And it typically works okay. And in fact, that's what I'm doing. That's what I use on my roof. Okay, so Scott, Scott, you got to speak up. How badly matched are rubber duck antennas?
Pretty bad, usually.
How bad? How bad?
I don't know. I think you have the answer.
Okay. Well, so here's the other thing. A quarter wave on 2 meters is 19 inches long. My antenna on my handheld is only 7 inches long. How do I get away with that? Because the antenna actually looks like this internally. This is a loading coil in the base. So that makes this total antenna 19 inches long, but physically only 7 inches long. So what does that make? What does that do for the efficiency of the antenna?
Makes it the same.
Oh no, because your maximum current is in this section here, but it's all twisted in on itself. So how much energy actually makes it out of that bottom part?
Very little.
No.
Yeah, very little. Right. Now you can get a full-size quarter wave antenna, which works a lot better. But if this whole thing is only 7 inches long, what you have is something called a rubber ducky. What's nice about it is that it's typically flexible. It's not going to jab you in the rib cage. But if you're trying to get into a distant repeater system or talk over a long range, it might have a gain of negative 10 dB. Right? That is not called gain anymore. That is called loss. So, and that would be compared to like dBi or something. So that is a very, very poor antenna. If it's negative 10 dB, that means that you have 1/10 of your power actually coming out as RF, which means that for every 1 watt in, you get 1/10 of a watt out. Not very efficient. Okay, so let's see. Go back to okay. The antenna gain, we talked about that. A beam antenna is something that concentrates signals in one direction. Ooh, I like that. Clarence Beam. I've never noticed that. A Yagi was named after Yagi and Uda. That's a type of beam antenna. What's nice about it is that it only has one driven element, so it's still easy to build. The parasitic elements out in space, they being the longer and the shorter elements, make it directional. Let's see. What happens if you use an antenna like a rubber duck antenna inside a car? The car behaves like a Faraday cage, and it captures most of the signal before it even gets outside. 5/8 wavelength antenna is better than a quarter wave because it has a lower angle of radiation and it has more gain. Feed lines. Okay. Coaxial cable is used because coaxial cable is cheap. It can be buried and it's really easy to lay on the ground. I have some outside getting wet. I don't care. It's waterproof. But what's the most important thing about coaxial cable? Keep it dry. Water is the enemy. Water causes oxidation. If your cable gets wet inside, it won't be good anymore. Your SWR will go up. It will burn up all its energy as heat. Okay, so it's important to draw coaxial cable. This is coaxial cable. This is coaxial cable. It has a center conductor and a shield. And outside of this shield, there's typically some kind of waterproof jacket. Ideally, this jacket is also ultraviolet proof. And why would we make it ultraviolet proof?
So the sun won't eat it up.
Well, and the sun doesn't crack it. So if it cracks, what happens?
Water
gets in.
Water gets inside, destroys the cable. So there you go. Okay. So this is coaxial cable. It's important to note that the shield is usually braid and or foil, like aluminum foil. And what's significant about that is that you can actually have one conductor and two conductors and a third conductor, which is on the outside. Radio frequency energy travels on the surface of wire. It doesn't go into the center very much, which means that the braid on the outside is actually thick enough to have separate currents on the inside and outside. We call this the skin effect with wire. I don't know why it did that.
I got a question for you on the coax cable. Does it matter if it's just out or if it's a direct bury cable if you bury it for the purpose of an antenna?
Not really.
Okay.
Okay, so basically
I'm here in
you have
Texas, and even if it's UV proof, it ain't UV proof here.
Yeah, good cable will be. It'll be okay. At least for a few years. Okay, so we have center conductor, we have our shield, and we have the jacket on the outside. So what's important to note is that we now have, if you look at how this is built, we have a center conductor and a shell that looks like that. This is spaced equally at all points within that shell. So if I have one conductor separated by a space from another conductor, what is that called?
Capacitor.
That's a capacitor. Okay. And if I have a piece of wire and another piece of wire, every piece of wire, whether it looks like this or is straight, has what?
Impedance.
It has inductance. Well, I have a capacitance and I have inductance. Okay. Well, I can actually model how this thing is built looking like this. So that is a series, that cable is a series of capacitors and inductors. And actually, I can split the capacitors in half, and I can split this one in half. And now I have these sections, which all look the same, don't they? This is a section, this is a section, this is a section, and this is a section. Those all look the same, right?
Yeah.
Okay. I have at a given frequency, I have a certain impedance for each one, but it turns out that the frequency actually ends up not mattering. They cancel each other out. And I end up with a Z characteristic. I ended up with a characteristic impedance based on the spacing and the size of how the cable is built. And that is how we get 50 ohm cable or 75 ohm cable or 90 ohm cable. So because it is a proportion, it's proportional to how this cable is built, I can have 50 ohm cable that is this big. I can have 50 ohm cable that's this big. Both of these are 50 ohm cable. How are they different? Give me some ideas. How are they different?
The distance between the center and the outside.
Yeah. Okay, so these can handle a higher voltage difference. That means this can also handle higher power. It also has larger conductors, which means it
Different
can handle
gauge.
higher power. What else?
Different gauge wire.
Yeah, okay. That's higher power and higher voltage.
Yeah.
What else?
Different insulating materials.
You can use different insulating materials, but physically, what is most important between these two different cables? If I use copper for both, if I use polystyrene or polyethylene for the gap, for the dielectric, what is most significant about these two cables?
Ease of use.
Yeah, true. Like the bigger one could be 6 inches in diameter. And that actually it's called hardline, and that does get used. How about other things?
Length.
Flexibility.
Flexibility. If the bigger one is called hardline, these come in 10-foot spools, okay? And they weigh a lot. But how about other things?
Weight, wind load.
Weight, wind load. How about if I were trying to run a 20,000 watt TV station?
It'd be a fuse.
Which one? Which one would I pick?
The big one.
The big one, yeah, because it can handle a lot more power. In addition to that, which one is going to give me the least loss? As it turns out, what we have here is somewhere a loss table. I have to find it. There we go. Cable loss per 100 feet. Let's just pick one frequency. Let's go with 14 megahertz. RG58 is your typical, what I had when I had a CB radio. It's your pretty cheap cable, 1.7 decibels of loss per 100 feet. Let's look over at LMR 240.91. Let's go to LMR 400, half a decibel of loss, which means that as your cable gets smaller, the losses are worse and worse. As your cable gets worse, as you go up in frequency, it gets much worse. So notice, let's just pick RG, let's pick LMR 240 right in the center. At 3.5 megahertz in 100 feet, how much loss is there?
1.45.
0.45. Essentially nothing, right? Let's go up to 440 megahertz. How much loss do I have?
5.2.
That's almost 6 decibels. Okay, so who was doing the calculations of decibels and power loss with me yesterday? That's almost 6 dB. Every change of 3 dB is how much power?
I don't want to play that game anymore.
3 dB. 3 dB is how many times?
10.
2 times.
2 times.
Oh,
Gotta
2 times.
memorize that. 3 decibels is 2 times. So if it's 6 dB, that's 2 times, and then another 2 times. It's 4 times. But it's lost, so it's negative, which means that of the 1 watt that you have going out, you get a quarter watt out of the cable in 100 feet. Where does the other 3/4 of a watt go?
Heat.
Heats the cable. Okay. If you have 100 watts going out, you have 100 watts going into the cable. You have 25 watts at the antenna. Where do the other 75 watts go?
Out as heat.
It goes out as heat, heats your cable. How about if you have 1,000 watts going out? You have 250 watts at the antenna. How much is going into your cable?
Same amount.
750 watts, right? Which, depending on what's going on, might be enough to destroy the cable, which is why they have power limits. So that's one of the reasons they have power limits. The other thing is you're basically burning up 3/4 of your power as heat. Now let's switch from at 440 megahertz from LMR 240, which is actually good cable, to LMR 400.
That's what I run is 400.
There you go. We go from 6 dB down to about 3. What does that mean if you change from 6 dB down to 3 dB? 3 decibels is how much?
Double.
That's right. So basically, now you're only losing 50% of your power. So if you have 100 watts going out into the cable, you have 50 watts going into the antenna instead of 25, just by picking a different cable.
Can you see this? Do you know what it is? Okay,
Which it looks like RG 174.
174. Thank you.
It's very, very small, and it's great for short runs.
Very flexible.
Very flexible, but also very, very small. I'd use it for 6 inches. All right. Let's see. So, all right. So now we're into connector types and protecting cables. Okay. So what is the enemy of coaxial cable?
Water.
Water. Okay. So how do you prevent water from getting in?
Seal it.
You seal it. Yeah. Okay. What happens if you have cable that is filled with air instead of a solid material? So let's say that you have
it'll get interference.
Yeah, no, it's fine. Let's say that you have a 1,000-watt system, and here's your tower, and you have spent a lot of money on this tower, and you put up an antenna that is a very expensive antenna, and you don't want to waste your energy that's going up into this antenna. So you might have a pigtail here, which allows it to rotate. Going up the side of the tower, you decide to put in 4-inch hardline because you have a lot of money to spend on this. Right? The hardline internally looks like this. Here's your center conductor. It has these spacers that keep it equally spaced. And here's your very, very heavy gauge wire. So this stuff might weigh, I don't know, 10 pounds per foot. Well, this is mostly filled with air to keep the weight down. Air is actually a really good dielectric too. So how would you keep water from getting into that? Considering it's air. And
fill it with gas.
You fill it with nitrogen gas. Exactly. You basically have to dry your air that's going into it, which means you have to have a pressurized system. So That's why most people, unless you happen to run like a TV station or something like that, don't get into that because it gets really expensive. But that's air insulated hardline. All right, now we're into connectors. Connectors are also really important because once you have a piece of cable, you have to figure out what to be able to do with your signal in order to get it into your antenna and out of your radio. So what we have are connectors, and the connectors look something like this. Can everybody see that?
Yes.
Yeah.
Okay, so we have different kinds of connectors. Notice this actually on the right-hand side is one of the best tables I've ever seen because not only does it show what the connectors look like, but it shows the typical operating frequencies at which you can use them. Notice the SMA connector. This is actually a very, very good connector. It's very small, but it's also it's also good up to over 10 gigahertz. Right. This is typically what you'll find all the way on the left-hand side in most handhelds today. Now, oddly enough, on all the way on the right-hand side, what do you see that connector called? I don't know if you can see my cursor or not, but
UHF.
UHF. Okay, what does UHF mean?
Ultra high
Ultra high
frequency.
frequency.
Yeah, okay, but the UHF band starts at 300 megahertz. What do you notice about that connector? It's good up to 300 megahertz. It was basically named that before we really understood what UHF really was. That's a very old connector, but it's very easy to solder. It's easy to put together. And we typically will find that on the back of most HF radios. What frequencies are HF again? 3 to 30 megahertz. Perfectly good for that. Easy to work with. And so that is the most commonly used connector that we find on most equipment. Notice also on the left-hand side, we have this thing called an N connector. That's a double shielded and in theory, waterproof. It's got gasketing built into it connector. If we're going to be using UHF or microwaves, we typically use N connectors, sometimes SMA. Okay. What can cause erratic changes in SWR? Has anyone ever noticed that they have if you have a cable TV system and your picture is kind of like, blocky or fuzzy or something like that? Has anyone ever noticed that? And then you go to the back of your TV and it turns out you have a loose cable. I've found that. Those connectors tend to loosen up. Basically, what you have is a poor standing wave ratio, and a lot of the signal that should be getting into your TV is not. And what you end up with is signal loss at that point. You have a high standing wave ratio. All right, standing wave ratio is a measure of how well a load is something that uses power, is matched to a transmission line that delivers it. Perfect SWR, a perfect match is 1-to-1. That is right there, 1-to-1. An SWR of 4-to-1 indicates that you have an impedance mismatch. It's a bad match. A low SWR means that you are efficiently transferring power from one device or one part of your system into another part. Notice this reduced signal loss. What happens to power lost? Everyone?
Heat.
It turns into heat, right? If you live someplace cold, that could be useful because it'll keep ice from forming. But ideally, you're not going to be doing that because there are cheaper ways to do it. Why do most solid state transmitters reduce power output? To keep you from developing too much voltage, to keep you from developing too much voltage on your transistors. You don't want to blow them up. They typically will let their smoke out. Once the smoke is gone, they don't work anymore. Again, magic smoke. When choosing an SWR meter, SWR again is standing wave ratio. frequency and power level at which the measurements will be made, because these are essentially these essentially use like tuned components, and they typically are set up to operate in a certain range of frequencies. The one that I showed you a picture of before, that antenna tuner, also has a standing wave ratio meter built into it. They specifically say that this tuner is useful for up to 50 megahertz because of the componentry used, not above that. If you want to have a meter or a tuner that is operated at 144 megahertz or 220 megahertz or 440 megahertz, it is different componentry. Higher speed diodes, things like that. You can also use a directional watt meter, because we're really measuring forward energy and reverse energy going back the other way. You can use something called a directional watt meter, which basically is able to calculate the energy going out and energy going back. Once you have those numbers, you can actually, if you really want to, calculate what your SWR is. You put an RF meter in between the transmitter and the antenna. How about if you have an antenna tuner, right? We have that magic box again. So I'm going to draw our transceiver, XCVR, and here's our antenna tuner, and up to the antenna. And let's say I have 50 ohms here, and this is 200 ohms. And I have tuned my antenna tuner so that my transceiver is happy. I am going to put a watt meter right here, an SWR and watt meter. Going to go right there between the transceiver and the tuner. Sometimes your watt meter and SWR meter will be built into the tuner. If it's a manual tuner, that's typically something you have to adjust by hand. That is very often the case. So let me ask a question. Let's say that your tuner is now tuned so that it looks like 50 ohms, and your transceiver is 50 ohms, and your cable is 50 ohms, and this is 50 ohms. What's your standing wave ratio at the antenna?
1 to 1.
1 to 1.
It is not. It is 4 to 1. Why is that?
We haven't adjusted the antenna.
Yeah, you haven't done a thing up here. You still have a mismatch here. What is the only thing that has changed?
The connection between the transceiver and the tuner.
Your transceiver is happy, right? You still have a mismatch, which is why ideally the first thing you're going to do is figure out what's wrong with your antenna, if there's a reason to, if there's an ability to do that. If you can't fix it because you're operating off of the resonant frequency, then, okay, you're okay with it. The transceiver's still going to be happy. You're going to accept the fact that you have losses. The other thing you can do is, let's say that you have the option of cable that is 3 dB per 100 feet or 0.3 dB per 100 feet. If you can afford it, which one do you go for?
0.3.
Yeah, you go for the better cable, because signal that goes up and down and up and down and up and down, every time it passes through that cable, it experiences these losses. So if you have really bad cable, let's say that your cable has a loss of 10 dB per 100 feet, and you're measuring your reflected power way down here, how much of your power actually makes it back to the tuner? Almost nothing, right? So your SWR actually looks pretty good, but it's really not. So bad cable, lossy cable, masks actual problems. So that is something to remember. Bad cable masks problems with your antenna. That make sense?
Sure.
It does.
Can't you
Okay.
just measure your antenna ohmage and see, okay, it's wrong, and then change it?
Well, yeah, but what if your antenna is a fixed antenna hung between two trees? Like mine. What if your antenna's hung between two trees? What are you going to do then? I mean, I have two antennas to choose from. I have a bigger one and a smaller one, but that's all I've got. I don't have, because we have how many different frequencies we operate on? Look at all these different frequency bands, right? I don't have a separate antenna for each of these. So I rely on my tuner to get me access to a lot of these frequencies. The bigger antenna is tuned for 80 meters and the smaller antenna is tuned for 40 meters. All the other bands I get on, I have a tuner for, because I'm not sure what the impedance really is. I mean, if I had room, sure, I'd put up a different one for every band.
Does the antenna tuner go at the antenna or at the transceiver side?
Ideally, it goes up at the antenna. But if that's the case, what does that mean about your tuner? Think about where it is.
Too far away to use.
No, you can do it.
I
mean,
guess, yeah.
you can have a remote tuner, but what does it mean about it?
It's out in the weather.
It's out in the weather. And what else? Because it's probably going to be electrically operated. What does that mean?
Water is the enemy.
You got to run power to it. Yeah. And it's got to be waterproof, weatherproof. And, what if your antenna's up in a tree? Where's your antenna tuner?
Up in the tree.
In the tree.
And how much is it light? I don't know. Depends how you built it. If it can handle 1,000 watts, it's probably not small, which means you have to put it somewhere. So there are, again, lots of trade-offs. Ideally, yes, it's as close to the antenna as you can, but practically speaking, most of us don't have that luxury. Again, everything is a compromise when it comes to doing this stuff. You do the best job you can, and if you figure out a way to do it better, then you do it that way. There are companies that make remote tuners. There are companies that make antennas that are able to be tuned to be resonant on any frequency, pretty much any frequency you pick. They have a lot of moving parts. The antenna basically has motors built into it. So if the antenna has motors built into it,
cost a fortune.
That's right. It's called a step IR. If the antenna has motors built into it, what does that mean? You need to run the motors.
Power for the motor.
You need power to the antenna itself, to the motors, and that has to be controlled from somewhere. So there's a remote cable. I've used one of these antennas. They are fabulous, but they also require maintenance. They have moving parts. They have moving parts that are out if you live in some place that gets cold. They have moving parts that get hit by ice and snow. Can they freeze solid? Yep. If you try to move something that's frozen solid, what happens?
Breaks it.
You can break it. Yeah, exactly. So again, everything is a compromise when it comes to this stuff. You figure out what works best for you, and then you go with it. And if you come up with something better, you change it. And if you are happy with the way it is, you use it. I mean, I know I could put up a better antenna than I have, but I haven't because it's a lot of work. The gain that I get would be minimal. And what I have until the squirrels queue up my ropes and make the antenna fall, they've only done it to one of the two so far. Then I'm just going to leave it up there until it falls down and I have to do it again. So, all right, we are almost to a break. The purpose of a dummy load A dummy load is a non-inductive wire wound resistor mounted on a heatsink. Its goal is to simulate an antenna. How many ohms do you think a dummy load should be?
50.
50 ohms. That's right. And it's called wire wound because it's basically wire wrapped in a ceramic coating. But how come it's not wire wound into coils? It's non-inductive. It looks like this. Keeps going back and forth without ever completing a coil.
Oh.
Why is that?
So it doesn't induce a voltage.
It doesn't have an inductance. It has inductance, but it's a very low inductance. This has high inductance. This has low inductance. What's my impedance? What's the formula for impedance? Z is equal to R plus I times X. This has XL is 2 pi FL. All right. So what do you see that F? What does F stand for there, everybody? Frequency. What if my value of X changed every time I changed frequencies? Would I still be at 50 ohms? I want a 50 ohm load, right? It would change every time I changed frequencies. So if I were to draw, and this is why it's important to understand this graph, my R is 50 ohms. It's right there. But my X might be here, or here, or here, or here, or here, or here, or here. My impedance is how long this line is. Ideally, I want it to be this flat line. If I have a high inductance, it could be way up here. That could be 100 ohms. Is that 50 ohms anymore?
No.
Nope. That's why we do non-inductive, but wire wound. So that's why, because anytime you complete a coil, anytime you complete one turn of wire, you add in a lot of inductance to it. A coil makes a magnetic field much better than a straight wire does. All right, how about a 5-minute break, everyone?
Work.
Does that work?
Yep.
Okay. Think of questions.
Later.
Yeah, I've got a question about the coaxial cable again. I know on a coaxial cable, you got one wire coming out of the end. Does a dipole have a special connection to receive that?
I think I can answer that.
All right, please do.
Yeah, well, basically, the simplest way you could do it is you take your coax, and on the end connected to the antenna, you just simply clip, well, you have that open end and you strip off the insulation. Then you kind of peel off. I mean, like the shield is braided.
Right.
Okay, it's braided wire. So what a lot of people do is you take some sort of a very sharp instrument. It could be a toothpick or I don't know, some sort of a pin or that you can manipulate, and you kind of pull those braids apart. So you get straighten out all the little tiny wires that make up the braid, and then you twist. And once you've done that, you kind of unbraid it at say along a couple inches, and then you twist all those little pieces of wire together, and you kind of create one big wire from that. But it's a straight wire now, and it's separated out from the main, the inner part of the coax. And the inner part is that you're going to have plastic around the inner conductor, and you strip that plastic away. So now you've got exposed inner conductor, which is just a regular wire. Could be solid wire, could be braided wire too. But you got the end of the shield, which is now straightened out and twisted together to form kind of a wire of its own. And then you connect each side to one leg of the dipole. Okay, so imagine you get your center conductor, you connect, you attach that to say the left leg, and then the shield is now connected to the right leg, and that's pretty much it.
Okay.
Yeah, that's really all you have to do. Oh, there's Scott. He can show you. I mean, that's a simple way. It's not the best way, but it really
works fine. It works fine. You know, the purists will say, well, you really need a balun. You really need something to balance out the currents on both, because they're not going to be exactly the same. Right?
Right.
Right,
Okay.
Scott?
Yeah.
A purist will say you really need that. A purist will also say you need to keep the shield from becoming part of the radiator, because again, we have something called the skin effect. So we have actually 3 current carrying conductors here. We have 1, we have 2, and we have 3. And if you don't want your outer part of your cable radiating, you have an unbalanced current traveling this way. And what you can do is you can wrap your cable in this donut-like device, which is called a ferrite. So your cable will pass through the ferrite. And as it does that, the magnetic field that the outer current number 3 generates will induce heating in the ferrite and warm it up, and none of the current, or very little of the current, will actually get through to the other side. So it essentially ends the current carrying ability of that outside conductor at that point. And that's known as a choke.
Okay.
The other thing you can do with it is, this is what we often do with like microphone cables and stuff. We'll have that same kind of ferrite, which looks like this, which is a donut, and we'll take our microphone cable or USB cable or whatever and go like this, and go out around the outside, and then go around it again, and around it again, and around it again, and around it again, and come out the other side. The more times you wrap it around that cable, the more times any induced current will be choked off before it gets to the device it's supposed to get to. And we actually have these all over the place. You may have seen one before, and it looks kind of like this. There we go. Stop share. Can everybody see my screen? Here's a power cable. Oh, what's that? Everyone see that?
Oh, yeah.
That is a ferrite choke on my laptop power cord. Its job is to take AC, and in particular RF, and choke it before it gets into my computer. Because computers operate on DC power. They don't like AC. All right, everybody ready to go?
Yes, sir.
Okay. Questions before we move on?
That antenna step IR, is that spelled STEPPIR?
Yes, it is.
Thank you. Thank you.
I have a quick question, Scott.
Yep.
Yep. So we talk about the antenna, and then the antenna getting into coax, so your coax can get into your transceiver. I'm looking at an antenna now for doing some QRP stuff. It's a end feed half wave, and it's the way the guy sells it. He sells it and he says you connect it directly to your transceiver.
Right.
Are you going to talk about that a bit, like the difference of like having an unknown and or not, and having coax between your transceiver and your actual antenna? If so, then I'll just listen.
Well, it's here's an N-fed antenna. Go away. Not answering that. Okay, so here's an N-fed antenna. It's still a half wave long, right? It's still basically a dipole, except that it's a dipole fed way, 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 way off the center. So what happens is your current distribution still looks like this. Your voltage still looks like this. I did that badly. Your voltage still looks like that. And instead of feeding it in the middle, you're feeding it way out here on the end where your current is very low and your voltage is very high. So we can do V equals IZ. And so we now have Z is equal to V over I, which is small large divided by small qualitatively. So you have a very high impedance. You're feeding at a very high impedance point. So again, the only way to do this is this might be 2K ohms or 2000 ohms. How do you feed 50 ohm cable with 2000 ohms?
Balloon.
Well, in particular, it is a balun transformer, which is a unbalanced transformer. But instead of being like, okay, so let's say I have a ferrite core, which is just a piece of iron that constrains magnetic energy, and I do this 1, 2, 3, and on the other side I do 1, 2, 3. What's my turns ratio?
1-to-1.
1-to-1. That means my impedance match is a 1-to-1 matching transformer, right? We can do this. It separates our one side from the other. I could also change this so that it's not 1-to-1. I could make this so that it on the other side is 1, 2. I could do that. So instead of having I have 3 turns on this side and 21 turns on this side. What would my ratio be?
7-to-1.
7-to-1.
49-to-1.
My impedance match is a ratio of n squared. So if my n ratio, my turns ratio is 7-to-1, what's my n squared?
49-to-1.
49-to-1. So if I have 50 ohms here, then I multiply this by 49. What do I get on the other side of my transformer? 50 times 50 is 2,500. 50 times 49 would be 2,450 ohms. So this would be able to match an impedance of 2,450 ohms to 50 ohms. It's pretty darn close. So maybe I get 40. That works just fine. The magic of the end-fed half-wave antenna, which was not really popular more than a few years ago, is that if I have any antenna and I feed it near the end, what's my impedance going to be?
Real high.
Very high, because I'm feeding it very close to where the current is 0. My impedance is going to be very, very high. And it doesn't really matter if the antenna is this long, or the antenna is this long, or the antenna goes way off the page. And it doesn't really matter what my wavelength looks like. It could be this, it could be this, it could be this. It's still being fed all the way over at the left, right? My impedance is still very high. It doesn't matter. The impedance is very high. So if I have a transformer that can transform qualitatively very high to very low, it works. That's the magic box in an end-fed half-wave antenna. It does
Can I ask
not work without that magic box.
Can I ask you another question?
Uh-huh.
Well, actually, two. What's the difference between Ballon and Unun? And first draw your when you first draw your EFHW there, you had the half wave, and then you had the current wave, if you want. Um, and is this what I want to see when I tune my antenna? That second wave there moves to the right to get more to a 1-to-1 ratio, or what is?
Yeah, that's a little more advanced.
All right, we'll talk about it
Yeah.
another time.
Okay.
Thank you.
Yep. Okay, so moving on, we're into modulation and signal bandwidth. Okay, so in order to do this, what really helps is that we are going to unshare that and share this and make sure we're sharing the right thing. Nope, wrong thing. Darn it. I keep picking the wrong thing. There we also the wrong thing. Jeez. I'm 0 for 3 now. Who didn't sleep well last night? There we go. Yeah. Okay. So we're going to go back to a web SDR. So the concept of signal bandwidth comes from essentially putting information into a signal. So if I just picked a signal, which was just a single pitch, a single tone, a single frequency, and I just turned it on and left it on, what would that tell you about anything other than there's something there?
Wouldn't tell you anything.
It doesn't tell you anything, exactly. It tells you absolutely nothing. So what we're going to do is make sure that I turn on the sound. Here we go. Okay. So if I just heard a single pitch of a tone, that would tell me absolutely nothing. What are some things I can do to make the tone more interesting? I can make it louder. I can make it quieter. What else?
Increase the pitch. 440.
I can change the frequency. What else can I do?
You're transmitting or you're receiving?
Well, we're receiving right now. What are some other things I can do to change a signal that is basically just it basically just sounds like a single tone? What are some ways I can interrupt?
You can clean it.
Yeah, I can interrupt it. What else? Something that could tell somebody else that I was there. I could change the pitch. I could bounce back and forth. If it's a wave, I can change the phase of the wave. Somebody else could be able to detect that, right? I could do this. Here we go. Okay, so what is this right here? What is that we were listening to?
GW.
That's Morse code. Okay. What makes Morse code? What makes Morse code have information?
The pulse.
Yeah, the fact that it's being turned on and off at a certain rate.
Yeah.
Okay, so let's look at another signal and do the same thing. Sure, walk away.
Ready till tomorrow. Okay, I walked out of the car and tell the wife. She says, couple colorful words. She says,
okay, so what are we doing here? What makes that signal have information? At its heart, that is just a single pitch. What are we doing with it?
Modulating it.
That's called single sideband. We are modulating it with a voice and putting audio. And what you're basically seeing is a spectral analysis of all the audio that is being transmitted. Now, what do you notice about it? Down there at the bottom is a scale, 28405 to 28408. This is measured in kilohertz. So how much space does that signal take?
3.
3 kilohertz. Okay. So if we pick another one, we will find, we'll take another listen. Sure. Again, disappear when I need you there. Any idea what that is?
That is a question I have.
That is interference. Quite likely being generated by like a power supply somewhere. It could also be over the horizon radar. Okay, so this is another signal. Notice that one is about 3 kilohertz wide. This is single sideband. So categorically, what could you say about the bandwidth of a single sideband signal is how big?
About 3 kilohertz.
3 kilohertz.
About 3 kilohertz. Okay, so now we're going to take a look at Morse code. Here we go. We're going to listen to this one. Okay, and how much space does that one take?
1 kilohertz, plus or minus.
Well, less than that.
Yeah.
So that's about 200 hertz wide, 300 hertz wide. But you notice, like this one right here, you would think that if it were just a single tone, it wouldn't take up any space at all, right? Right? Doesn't that make sense? I mean, it's just a tone. It's going on and off. But notice that it actually seems to take up a little bit of width whenever the on and off happens. And that's because it's being turned on and off. And this is actually a part of information theory that says that any signal that contains information uses bandwidth. It's kind of a mind-boggling thing, but to be able to see it for real is really kind of amazing. But by and large, a Morse code signal will typically fill 100, 150 hertz, which is about 1/20th the width of a signal that we were just listening to on single sideband. We could also listen over here. This is known as FT8. And what we have here in that same 3 kilohertz that we would listen to voice with, every one of these vertical stripes is another digital signal, which is one station talking to another. And each one takes up about 50 hertz. And this is a very low speed digital mode. We can look at another one. So what would the bandwidth of this signal be looking at that scope? It goes from about 28, about 500 hertz, right? Digital signal taking up about half a kilohertz. So obviously bandwidth is a real thing, right? A signal that contains information takes up space in the spectrum. So that's why I love having this web SDR stuff at my disposal. So let's say that we were now to take a look at
question about WebSDR and the waterfall.
Yep.
Is there a glossary of what those different signals look like, what they're actually producing?
There are lots of repositories that people have made online about what individual signals look like, but you'll have to look that up on your own.
I haven't come up with enough words to find it.
Yeah. Okay, so 0 frequency up to infinity, we're going to look at a little piece. Okay, we're going to call this our center frequency. This is where our radio is tuned. Looking at a signal in time, this is a sine wave. That's called a carrier. It's just a single wave at a single frequency that goes on forever. So we can change this by taking that carrier and modulating it so that it gets bigger and bigger and smaller. We are changing its amplitude. This has a name. This is called amplitude modulation. Amplitude modulation has a center frequency and creates sidebands that look like this. that's spread above and below the center frequency. Because every signal that has information takes up space. This has two different names for these two different sidebands. These are called the upper sideband and lower sideband. And there's also something called a carrier. The carrier frequency is a marker that tells you where it is. It provides the energy for being able to decode the signal. However, since it has no information in it, if you can regenerate it at the receiver, you don't need to transmit it. Well, as it turns out, also, upper and lower sideband are mirror images of each other. So really, you don't need to transmit one of these. You can pick which one you want to ignore. We will, for this case, pick the lower sideband and ignore it. And now we're doing something called upper sideband with a suppressed carrier. A full AM signal, which is amplitude modulation, was about this wide, 6 kilohertz. We just saw a second ago, how wide is that upper sideband signal?
3
kilohertz. Yes. Okay. So we have just basically sent the same amount of information in half the space. That's really important because what does it mean for practical terms?
More space for others to use.
More space for others, and what else?
Less power.
More efficiency.
More efficient, because if you were using your power to transmit this blue signal, you have the same amount of transmitter power available to you, which means that you have to waste some of it on transmitting the carrier, and you have to waste some of it transmitting the lower sideband, which nobody really needs because the lower and the upper are exactly the same. So the narrower the modulation technique, the less space it fills up, the more power you can dump into it, and that brings in something called power spectral density, which is how much power per hertz you can actually use. The higher the power spectral density, the signal might actually look this big versus a signal that looked this big. How do you think we measure the difference between the two? What units do you think we use? Well, there's decibels again. Why are decibels good? Because
ratio.
It's a ratio. We can figure out how many decibels stronger our signal will be on one end of the channel, on the other end of the channel, compared to the other signal that we could have transmitted. So let's take a really narrow band signal and compare it to single sideband. Okay, so here's our spectrum. Here's our center frequency right here. Here's our single sideband signal. We have, let's say, 100 watts available to us. And how wide is this signal? How much space?
3 kilohertz.
3 kilohertz. Okay, instead of sending this, we managed to pick a mode that is this wide. We'll call that Morse code, also known as continuous wave. But we have that same 100 watts available to us. How high could we use that same amount of energy filling that space? It might be like that. We might actually, we still have that same 100 watts, but it's in a narrower area on the spectrum. So compared from here to here, we might have a gain of 10 dB. What is 10 dB? How many times is 10 dB, everybody?
10 times.
10 times. It has the effective power of 10 times, which means that if it's 10 dB stronger, how about after it travels across the world, which one has a greater chance of being heard? The Morse code. How about if I could come up with a signal that's even narrower than that? How about if I could do something that had a bandwidth of 31 hertz? and Morse code had a bandwidth of 150 hertz. I'm now dumping that same amount of power into something 1/5 the size.
What mode is that?
This is called PSK31. It's phase shift keying and it's keyboard to keyboard. It's a digital mode that actually transmits at about 31 hertz, 31 baud. So it's basically typing speed. And that mode will give you 5 times as much power, or a gain of about let's see, what would it be? Probably, let's see, 6 times. So maybe 7 dB improvement over Morse code. When that goes across the world, which one gets heard first?
PSK.
PSK. So all of these things are important to understand because they all are measured in decibels and they can all be related to each other. So now we're going to look at frequency modulation. Okay, those are all amplitude modulation, although PSK is phase modulation. So we're going to take a signal, and instead of modulating the amplitude like this, we're going to modulate the frequency and always keep it at the same amplitude. This is called FM. So essentially what we're looking at is a carrier frequency, which is kind of a 0 point, and we have lower frequencies here and higher frequencies here. And the rapidity with which those change determines what the frequency that we're listening to is and how far it spreads on the spectrum. What this ends up doing is this causes a center frequency here, and it causes modulation sidebands that are roughly the same amplitude. Covering 10 to 15 kilohertz, not 10 to 15 hertz, but 10 to 15 kilohertz. So compared to, here's sideband. What's the bandwidth of sideband again?
3 kilohertz.
3 kilohertz. What's the bandwidth of Morse code? About 150 hertz. Which is going to be the least efficient?
The FM.
FM.
That would be FM. FM is also very, very quiet and noise immune, but it's also, it uses, first of all, a lot of room. It uses a lot of room on the spectrum, and which is going to be the last signal to be heard?
FM.
FM's going to drop out. So we consider these other signals to be weak signal modes. These are called weak signal modes, especially on bands where we use a lot of FM, such as 2 meters and 70 centimeters. These modes are called weak signal modes because when the signals are weak, they are used where FM doesn't work. And FM is so popular because, why is FM so popular?
Very clear.
It sounds great. Because of the nature of FM, it's completely immune to noise. It's completely immune to lightning and static crashes and things like that. Very high fidelity. It's high fidelity because it takes up a lot of room. The more fidelity you have, the more bandwidth it takes up. How much? What's the bandwidth of a commercial radio station, which uses FM?
200 kilohertz.
200 kilohertz. Yeah. Again, more information, more fidelity takes up tons of space.
Carson's rule.
Yep. The other thing is we also have something called ATV, which is amateur television. This is called NTSC. We can also do digital TV if we really want to. This fills up that much room. 6 megahertz, not kilohertz, 6 megahertz. So where do you think we do that? What do you have to have in order to do something
ultra high?
Yeah, you need a lot of space, you need a lot of bandwidth because there's a lot of information being passed. So let's go find it. Here's the NTIA chart. Okay, we're going to look at this band. We need something that has 6 megahertz available to it. And there's broadcasting. There's broadcasting. And so right here in this amateur band, 420 to 450, this is where our first TV mode is. And in fact, you notice this thing that says amateur TV fast scan in light blue. Here we go. 426 to 432. That's a TV state. That's a TV channel. 420 to 426. That's a TV channel. Then again, higher up, 909 to 915, 915 to 921, 921 to 927. Those are TV channels. That's where we can actually transmit our own TV stuff. All right, any questions before we move on?
Yes.
Go for it.
Why FM is so popular for VHF and UHF and not below? I'm not talking about the band plan because I understand that the frequency bandwidth is smaller. But why do we use the FM on the VHF and not, for example, on the 30 meters?
Oh, well, okay, let's take a look at how much space there is. FM takes 15 kilohertz, right? This whole band from 24,890 to 24,990 is only 100 kilohertz wide. So one FM channel would take up 15% of that band.
Yeah, but pretend that the 12 meters band would be wider.
Well, if it is, notice, let's go on 10 meters, 28 to 2970, 29,700. We have FM channels because there is more room available.
Like the Citizen band, for example, the 11 meters, they do use the FM. So it's not, a technical limitation on the frequency modulation. It's
No.
Because we have a smaller space, we have to stay within those spaces. So the modulation is different. We don't use the FM, but we use something else.
Right. We want to make the best use of the bandwidth we have. And for the most part, FM is not efficient as far as space goes. So you want to put it where there's the most room to do it, which is why we do that. That and the fact that a lot of the early equipment on VHF and UHF, even back in the 1960s, a lot of the mobile equipment, handheld radios, commercial companies like Motorola would actually build FM handheld radios, FM mobile radios. And when no amateur companies existed to build the stuff, people would just get commercial radios and modify them.
Right. Okay, thanks.
Okay, let's see. So VHF and UHF voice repeaters typically use FM or phase modulation, which is PM. For VHF packet, this is a way of sending digital information over FM repeaters and over FM over voice, so FM or PM. Single sideband is a kind of amplitude modulation. Weak signal is single sideband or Morse code, either one. Okay, so looking at the frequency spectrum chart, there's a breakpoint right here at the 30-meter band, which doesn't allow voice at all because it's so narrow and because we have to coexist with other services that use it. 40 meters and lower use lower sideband. By convention, 20 meters and up use upper sideband. Therefore, on 10 meters, we would use upper sideband. Okay, we have bandwidths. FM. Okay, one disadvantage of FM suffers from something called the capture effect. If anyone's ever been on a repeater or used FM and noticed that if there were two signals there, you would hear a squealing sound. Very often you'll hear neither one of the two. At best, one person wins and the other person's obliterated. This is known as the capture effect, and that's largely because FM does not lend itself well to multiple signals being on the same frequency at the same time. Amplitude modulation, you can do that. We have conversations where you hear 2 or 3 people talking at the same time. That doesn't work on FM. CW, that's Morse code. It's another name for Morse code. It's continuous wave. An electronic key we covered yesterday briefly. Believe it or not, if you look at the chart, you will see that as a technician licensee, you have privileges on the high frequency bands. Now, you have privileges on 6 meters and higher automatically, covering everything. But notice you have this novice and technician voice. Novice license you can't get anymore, but a technician license you can. Notice this hatch right here, the blue hatch and the green hatch and the green hatch and the green hatch. You're allowed to do Morse code on any of those frequencies. So if you happen to have a technician license and you want to play around with Morse code, you can do that. All right, moving on. Digital modes. Okay. If anyone's curious, we're on page 61. We've got to get on our horse a little bit, but it gets less and less technical as we go. So digital communications modes. These are all digital. Packet radio. Packet is the original digital mode. IEEE 802.11 is also known as Wi-Fi, or it's what's used for Wi-Fi, and FT8. When sending packet radio transmissions, we use something called ARQ, which is automatic repeat request. We also send a header. Essentially, we're sending digital information over a handheld or mobile radio using FM. We also have information in the header, which says the signal, this particular message is going from this station to this station and go. So because it's digital, we also have error detection, and repeat request says if something got hacked, or if something got, I shouldn't say hacked, if something got damaged, if a signal got damaged in the process of getting from one point to another, it didn't match anymore, send it again automatically. APRS, that is the Automated Packet Reporting System. APRS is a hybridization of ham radio and GPS and geographic information systems. So it looks something like this. These are APRS stations in the greater Portland, Eugene metropolitan area. And basically any one of these things that you see is an APRS station. It could be in a car, it could be in a balloon, it could be a repeating station, essentially sending information, including who it is, where it is, what its GPS information is, whether it's moving, et cetera, et cetera. Oh, like here's one. You can change the icon. And this is actually then uploaded to the internet and placed on a map. This can be very useful for tracking like high altitude balloons or rocketry or stuff like that, as well as just, having fun or being used to put a little transmitter on somebody who's going for a run or a bike ride so people can track where they are. Okay, so that's APRS. PSK, again, is phase shift keying. We alter the phase of the signal. DMR is digital mobile radio. We basically have repeater channels that are 12.5 kilohertz wide. We do FM across them. However, if we can digitize the signal and make it a string of ones and zeros, we can make each of them take up half of the time. So that at time number 1 and 3 and 5, those would be the odds, one of those groups of people would transmit, and on 2, 4, and 6, the other group would transmit. We essentially take an analog signal and we make it, we reduce the fidelity slightly, make it take up less bandwidth, and then we can send them at opposite times. The nice thing about that is that if you are on and connected to one group or the other, you never hear the other stations, which allows us to use each repeater channel for twice as many communications at the same time. Makes better use of the resource. WSJTX, this is known for being the home of the FT8 digital software. We use it for weak signal beacons, meteor scatter, Earth, Moon, Earth, and lots of other things. FT8 again, what is it? A digital mode capable of low signal to noise operation. It's used for very, very, very weak signal stuff. What's cool about that is that map that I showed you guys yesterday, which was a map of the Earth with all the different bands that are connecting from point to point at all times, that is generated from people using FT8 and connecting their computers to the internet and reporting what they're hearing. A mesh. Okay, Scott. Hey, Scott.
Yes, I'm here.
Did you want to talk about mesh for a minute?
Well, you may be more of an expert than I am. Well, I'll just mention briefly, it is a form of amateur radio internet that's not using cables. It's not a cable system. It's an RF system. So basically, you would have a modem that's designed to be outdoors, and there's you go to a website called arden.org, I think, AREDN. I think you had it there, Scott. Which is the Amateur Radio Emergency Digital Network, and it's really it's operating up at 3 gigahertz and 5 gigahertz. I think even 3 and 5 gigahertz, and you download a firmware that you flash into your commercially bought router, which could be something like made by a company like Ubiquity. Microtech is another company, several others. And basically, you convert the frequencies that the commercial frequencies that are already programmed into that router to the ham radio frequencies that are allotted by the FCC. And these are in the same range. It could be 5 gigahertz frequencies, for example. And then, but they're not operating and competing with regular router frequencies. So you
I
put
have a question on this.
Yeah.
Okay, I have a network that spans 14 counties in the state of Michigan, all wireless. And we use exclusively Microtech for routing on our network. So you're telling me that we could flash a router, put it at the base of this, and turn that into a mesh repeater network for ham?
Yeah, I think all the routers have to be flashed.
Well,
yeah, the firmware is
different.
different.
But we could flash a specific router, put it on that network,
yeah,
in a 3
I don't see why
gigahertz
not.
or 5 gigahertz band, and turn it into a mesh repeater
Right.
for the ham operators around the world.
Exactly. Well, not around the world. It would be more local.
Local area.
These are line of sight. You have to aim these things. Each node, we call them nodes. So everybody who has one of these would have a node. The nodes have to be within a line of sight communication. And so therefore you have to strategically plan this so that one node can see the other node. And then sometimes if you're lucky,
we have all kinds of point-to-point backups running around the state of Michigan.
Well, there you go. You got it. Well, you should look into this. It's very well established and very popular around the world. So
I was curious. Question: are we allowed to operate that on like 6 gigahertz and 24 gigahertz and 80 gigahertz too?
Well, wherever the FCC allows amateur radio.
Well, because we've got licensing for all of that already.
Right.
Well, the technician license will give you that privilege.
So long as it's a ham band.
Yeah, it's got to be ham. So you have to check with the band plan. Well, of course, that can be done.
Well, the other thing is that one thing we haven't covered yet, because we haven't really done the rules and regs yet, is that we are not allowed to encrypt anything or do anything to hide the meaning of a message. So anything we do, we don't pay for what we get, right? We don't pay for all this access to all these frequencies. So in exchange for that, what we do is open to the public, which means anybody can listen unless you're controlling a spacecraft or something. or controlling a remote control plane, because nobody wants to take no one wants to see you have, it gets taken over, somebody crashes it. So we're not allowed to encrypt anything, but in times of emergency, you say, okay, well, which is more important, encrypting the information or making sure that somebody knows that somebody's alive? So
Right.
so that is potentially, like for instance, we can do high speed internet, over RF over a distance of 30 miles and connect a whole bunch of nodes together from point to point. There's if you know the topography of Oregon, we've got the Coast Range, which separates all the coastal communities from the Willamette Valley. And then we've got the Cascades, which separate the Willamette Valley from the high desert. And, to get communications from place to place over those mountains, you basically need to strategically put, router systems that will look down into the valley and then connect from mountaintop to mountaintop. So that's one of the reasons that people have been using Arden nodes, going from, strategically placed point to point, mountaintop to mountaintop. That's a backbone system.
Well, that's why I was curious about this, because we're up on 200 and 300-foot towers all over the state. So.
That helps. Yeah. That helps a lot.
Yeah.
Okay.
All right.
Go ahead.
Go ahead, Scott. Sorry.
No, go ahead, Scott.
I was just going to say to Steve, I'd be interested in finding out what you guys are doing there in Michigan, if it's not ham radio. So I just, because there's another thing called Meschastic, which is a commercial version of that. And a lot of people, even a lot of hams are getting into that, but it has certain limitations compared to the Arden stuff. So anyway, okay, I'll shut up. Scott, go ahead.
All right. Thanks, Scott. Not for shutting up, for your input. All right. Amateur radio station safety. Okay, so as we showed yesterday, you can do things that can hurt a lot of people. You can build a transmitter that has a 1,500 watt amplifier in it. Typically, this will use vacuum tubes to generate that much RF. Vacuum tubes that run on power can often run at 3,000 volts. 3,000 volts is enough to kill you very, very quickly and painfully. So there is a lot of stuff that is involved with safety. All right. First of all, electrical current flowing through the body can mess up your heart, make your muscles contract, and also burn you. In the United States, the black insulation on a wire indicates the hot conductor. We have hot, neutral, and ground on a 3-wire system. The hot wire is the black wire, neutral is white, ground is green. In order to protect against electrical shock, 3-wire cords whenever possible, connect to a common safety ground, and put mechanical interlocks in high voltage circuits like amplifiers. A fuse is designed to disconnect a circuit in case of overload. We have them in our fuse boxes or breaker panels. We also, if we build something, we will put a breaker or a fuse in series with the hot conductor only. So if we get a fault in our piece of equipment, it will break the power. It will disconnect the power. That's the same reason why you should never, unless you really know what you're doing, replace a 5-amp fuse with a 20-amp fuse, because the rest of the circuit is probably not designed for it, and you could actually burn something. Literally start a fire. Okay, power supply, after turning it off, typically we'll have a big capacitor used for a filter. Well, okay, capacitors store energy. When I was 9 years old, my dad gave me a 500,000 millifarad capacitor, or microfarad capacitor, which was about 6 inches tall and 3 inches around, from an old computer power supply. I wanted to see what it would do, so I charged it up with a 9-volt battery, and I took 2 screwdrivers and put them in the terminals and then touched them together, and I discovered arc welding. So, yeah, you can do a lot of harm with capacitors. Which of the following is a safety hazard of a 12-volt storage battery? Shorting the terminals can cause burns, fire, or an explosion. Okay, so this is a good time to briefly talk about batteries. Discharging or charging a battery too quickly can cause overheating or outgassing. Okay, so if we look at a 12-volt storage battery, most vehicle systems today are negative ground 12-volt systems. All right, negative ground 12-volt systems. Everybody still here okay?
Yes.
Okay. So the core of a negative ground 12-volt system is typically a lead acid battery, which contains a combination of lead, like metal lead, and sulfuric acid and water. So slightly diluted sulfuric acid. So one of the things that can happen if you overcharge or over discharge a battery that is like that is that it can evolve hydrogen gas. So what happens if you're trying to recharge a car battery that has been discharged or get a jump start is that you would connect the hot to the hot and the negative to the negative, right? That makes sense. You're basically jump starting a car, except for the fact that when you make that connection, it might generate a spark. If your battery is really discharged, what gas did I say was right there?
Hydrogen.
Hydrogen gas. Anyone know about the Hindenburg?
Yep.
Yeah, okay. So what happens if you get an explosion at your battery? What do you get a shower of?
Sulfuric acid.
You get a sulfuric acid bath. That's right. Okay. That's why it is a good idea to be very, very careful. And that's why I never connect. If I'm jump starting a car battery, I never connect to the negative terminal of the dead battery. I always connect to the frame of the car somewhere far, far away. People will also wave their hand back and forth to try to clear the air of any hydrogen gas that maybe is around there, because you really don't want an exploding lead acid battery. It would really, I know someone that happened to, and he survived it, but it was a harrowing experience to get not only the explosion, but a shower of sulfuric acid.
Been there, done that.
Been there, done that?
Yes, sir.
Oh, I don't like to hear that.
Well,
But
yeah.
you bet. Yeah.
We were charging a battery in an auto shop, and I just went over to check on it. I didn't do anything to it. And as I looked down, it went off.
Yeah.
And it showered me with acid and everything. And fortunately, I had a little kid there. Well, he was no little kid, but he picked me up by the waist and dragged me in and put me in a slop sink.
Yeah.
And hosed me down.
That was
And
good.
shirt, pants, everything disintegrated.
Yeah. So it's a real thing. The other thing is that it is important to note, now that we're talking about batteries, there are two kinds of batteries, essentially. There are primary cells and secondary cells. A primary cell is a battery that is charged once forever. Basically, when it's dead, like a carbon zinc battery or a lithium coin cell, button cell. Those batteries you buy an alkaline battery. Basically, when it's dead, you don't get to recharge it. A primary cell is a one-time thing. A secondary cell is a rechargeable battery that has a reversible chemistry in it so that you can recharge it. Essentially, if you think about rechargeable batteries, a battery is a way of storing electrical energy in chemical form, because energy can neither be created nor destroyed. So essentially, you're creating a chemical reaction that generates electricity. In order to recharge a battery, what you're doing is you're reversing the chemical reaction inside the battery, which is why batteries get old and sometimes they don't work as well as they used to. Which is why they have limits on the numbers of recycled charges and the depth of discharge and things like that. Lead acid batteries, nickel metal hydride, lithium iron phosphate, NiCads, those are all rechargeable batteries. Don't try to recharge don't try to recharge an alkaline unless it's specifically designed for it. It won't work. Okay, antenna and tower safety. When putting up an antenna, it's an important idea to look for and stay clear of overhead electrical wires. What kind of voltage do those overhead wires carry?
Very high.
17,000.
Yeah, at least 12,000 volts, right? In order to stay safe, you need to make sure that any part of what you are doing stays at least 10 feet away from those power lines, especially if it falls or if you're moving something at minimum 10 feet away from those power lines, because it will find a way to arc. Just a couple of years ago, actually, it might have been last year, there was a very well-known ham in Texas. They were taking down an antenna, and he saw it starting to rotate when it was being lowered, and he went to grab it, and the other end of the antenna was touching a high voltage power line, and he died on the spot. Lots of experience, and it's really easy to forget what you're doing sometimes. So even though he had lots of experience, he was killed instantly. So electrical power lines, stay away at all costs. Why should you avoid attaching an antenna to a utility pole? Well, it's not yours. It's a utility pole. And again, those high voltage power lines, 14,000, 17,000, 25,000 volts, shouldn't be up there.
Hey, Scott, can I
Yeah.
can I add just a little bit to this?
Yeah.
This one's kind of personal for me because this is the industry I work in, but we actually lost somebody local in the area last year after the ice storms. The we believe he was trying to clear debris that had fell on his guy wire system for his antenna
Mm-hmm.
and climbed up a ladder. We had sagging lines from all the ice. He got hit. Unfortunately, he didn't make it. So these are like real world problems. You know, people they're trying to do well. They're trying to do the right thing. What makes sense to them. But I'm going to just second what you said. Stay away from power lines because you're not going to make it.
Yeah.
The other thing that we see a lot of in industry is we see people tying into the utility grounds or cutting utility grounds. Don't do that. It's bad news bears for you.
Yeah.
You might make it in the short term, but I guarantee you in the long term, either you or your house isn't going to make it. So stay away from, just generally speaking, if there's a utility pole, stay the hell away from it and don't touch it.
The other thing is, let's say you have a power outage and you want to use your house wiring to distribute power from a generator that you have. Why should you not do that, everybody?
Backfeeding.
You will backfeed the system. Well, but my generator is only 120 volts. Well, it's an unfortunate thing, but transformers don't care which way the power's coming in and going out. So if you have 12,000 volts out on the power lines that is normally delivering power to your house at 120 volts, and you hook up a 120 volt generator, what are you doing to the power line?
Charging it.
You're energizing it to 12,000 volts. So what if somebody has turned off the power somewhere so that they can pull a person out of a car where a power line fell on? It took your power out, but then you decided to hook up a generator. What did you just do?
Charge your power.
Yeah, so they're trying to save somebody and you just recharge the power lines. So don't do that. Don't ever do that. Okay, an antenna. Why should you never touch it during a transmission? I've had this happen. You get something called an RF burn. It makes a little pinhole that turns brown or black, and it really hurts. When putting up a tower, tie off, never climb by yourself. Ever, 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 ever. Because what will happen if you have a heart attack? You'll be hung out there. What happens if you get stung by a bee and have a reaction? You're going to be hung up on that tower and you're not going to be able to get down. When using a crank-up tower, you have to make sure that locking devices are installed or you retract it first. A safety wire through a turnbuckle. You basically will put a safety wire through it because a turnbuckle will tend to vibrate and loosen in the wind. So the wire will keep it from rotating. Follow local electrical codes. And for grounding, you put For each tower leg, you use a separate 8-foot grounding rod. You bond them to the tower and to each other. When installing ground wires on a tower for lightning protection, a couple of things that are important to note. You want short, direct connections and no bends, because lightning does not like to go around right angles. Lightning follows gentle curves and lightning follows straight lines. If lightning encounters a 90-degree bend, it will more likely go and try to jump to the ground and create an arc instead of just following the cable. All external ground rods and earth connections have to be bonded together with a heavy wire or conductive strap. Lightning arresters should be installed right outside of your house on a grounded panel, all of them on one panel before they come into the house. A lightning arrestor is basically a lightning arrestor is a small box that your coax cable fits into, coax cable comes out of, and it has a little ground tab right here. And internally, there is a tube which is filled with a conductor that passes through it, as well as a gas. The gas is normally shielded and protecting or insulated from the inside to the outside. But what happens is if there's a really high voltage, suddenly like 20,000 volts, what will happen is it will jump this distance, the gas will ionize, and you end up taking all your power, hopefully, and sending it to ground instead of sending it down to your equipment. So that's a gas tube lightning arrestor. And once that happens, you go and replace the tube or replace the lightning arrestor. And hopefully it prevents equipment damage.
I have a question about those.
Uh-huh.
So these are installed at the union between your antenna feed and your transceiver?
Typically outside the house, right outside the house. You connect everything to a metal plate and then run that straight to the ground.
So it's midline in the coax feed
Yeah.
to your antenna.
Yes.
How does that get addressed or analyzed with respect to standing wave ratio and antenna tuning and all that?
They're typically designed for a certain impedance.
Okay.
So you buy it, it'll say, suitable for 50 ohms. Yeah.
Okay. And just you insert it and no problem.
Ideally, you never generate high enough voltages when you're just transmitting to ever arc anything over. They'll have a power rating too.
Right. Okay.
So to make sure of that.
Scott,
Thanks.
Yeah.
Why wouldn't you want to do like on all of our gear? We use one at the top, one at the base of the tower.
You can do that.
I mean, wouldn't you want to do that at your?
It's about cost.
Ham gear also.
It's about cost.
Okay.
I mean, you can put a whole bunch of them. It doesn't hurt, but I mean, every time you add something, it adds cost.
And those don't negatively affect transmission.
No.
Okay.
No. I mean, they'll have an insertion loss, but it's probably like 0.05 dB or something. Okay, radio signals. We're into RF hazards and radiation exposure. Okay, as we saw from our frequency spectrum chart, our electromagnetic spectrum, radio waves are non-ionizing. Well, we know for a fact that even though they're non-ionizing, they can still cause heating. Microwave ovens, that's RF energy. RF energy at 2.4 gigahertz roughly can heat water, right? Well, your body is 70% water. So if you were to go into a microwave oven, it would be a very bad day. So clearly it's not safe, but it's not as unsafe as, for instance, standing right next to an X-ray tube all day. X-rays are ionizing radiation. They will actually cause genetic damage. RF energy will not cause genetic damage. Okay. Who is responsible for ensuring that nobody is exposed to RF energy above exposure limits? That would be the station licensee. If you have an if you have a ham license, you are the station licensee. It's your responsibility to make sure that you have followed one of these three methods: FCC OET Bulletin 65, computer modeling, or using a field strength meter to go and check what your actual exposures are. More than likely, you will have used one of the exposure calculators because the other methods are really complicated. The calculations are not simple, but there are websites, for instance, that have been set up that you just plug in your information and it runs the calculations and it matches what the FCC says, and it makes it a lot easier to do. Cycle time, duty cycle, that basically means what percentage of the time are you transmitting? So if I have a 50% duty cycle, that means I'm transmitting half the time and listening half the time. If I have a permissible exposure limit of 1 watt, but I'm running only 50% duty cycle, that means I can run 2 watts when I'm transmitting and 0 watts when I'm not, so that the average over a period of time is safe. Why do exposure limits vary with frequency? Well, in the extreme, again, microwave oven. Water obviously behaves differently when exposed to different frequencies. The typical human body also has resonances, and the maximum effect that we get is at 50 megahertz, other than microwave radiation. So we have the lowest exposure values at 50 megahertz. So what varies to change RF exposure? If you have an antenna, for instance, that points in one direction and you're standing behind it, you probably won't get too much exposure. If you're standing below it, you probably won't get too much exposure. Also, the frequency and the power level and how far away you are, because if you're really far away, you could be a mile away. That's very different than being a foot away. If you're having problems with RF radiation, you find that your calculations show that it's not safe, you can put your antennas up higher. You can decide to change the time that you're operating. There's also something called there's also a difference between the general public and just you and the people who know what you're doing. Those are two different groups of people. When we are operating at the Eugene Science Center, I know when I'm transmitting what we are transmitting. People who are at the museum don't necessarily know what I'm doing. So what you have to do is take a look at, here we go, RF exposure calculator. So it's important to do is know that when you're doing your calculations, whether you are in a controlled environment or an uncontrolled environment. And this is just a website. Notice it's hint link power density calculator. So I can go and do another calculation. We'll say that we're running 50 watts. Oh, look, you got to know what the antenna gain is in dBi, which is compared to an isotropic. Notice it says enter 2.2 for dipoles. Let's say I have a dipole, and we are 3 meters away from the antenna at 28 megahertz. Are we safe, yes or no? There we go. So you take this, you print it out, you post it on the wall, you're safe, you're good to go. What this shows is that at that frequency, an uncontrolled environment, you can have a maximum power density of 0.23 milliwatts per square centimeter. And from the calculations, from the numbers you typed in, show that it's 0.18, which is less than 0.23. Uncontrolled environment means it's the general public. They don't know what's going on. So that's safe. Assuming that you're running 50 watts at 100% duty cycle. Notice there's that average power. So you could be running 100 watts a quarter of the time, and you'd actually be able to do even more. So it's important to understand this stuff. We're actually required to do an RF exposure calculation. And anytime you change equipment, you have to do the same thing. Okay, station setup. Okay, how about a
I have a question on that. Do you have to print that off and post it in your shack or on outside your house or?
Well, it depends. I mean, I don't. I've done it for my house. I know that it's safe. At the museum, we have it. You know, at our museum station, we ran it, we printed it out, we keep it in the drawer. Okay, in case anyone's curious, we show them this is what we have. These are the calculations we did. You can certainly put it on the wall. No one will fault you for it. But it's really to protect yourself and other people. And the general public who doesn't, that's even more important, to protect the general public, which is why, for instance, if you find an AM transmitting antenna out in the middle of the woods, there will be a big 300-foot tower, but there will be a fenced off area that says no access, right? Hazard. That makes it a controlled area. That's why that's there, because they don't want just anybody who doesn't know what they're doing walking up to it and getting a heavy RF dose.
So that's
All right.
power at the antenna for that calculation.
What?
That would be power at the antenna location.
Yeah.
Or transmitted power.
No, power at the antenna. So that's actually really significant, because what if you have a 100-watt transmitter and you have enough loss to make your antenna power 25 watts? Well, then you use 25 watts.
Okay.
All right. How about a break for 7 minutes? Come back at noon Pacific time. Does that work?
It works.
Lunchtime?
We'll call it a quick lunch.
Very quick.
Anyone have any questions during this downtime?
I could have a quick question.
Good.
Regarding ground. I was having this discussion with a city guy here, and he was adamant that any possible power loss going through the ground should go back to the grid and therefore should be connected to the electrical panel and not to a rod in the ground. One of his example was that, well, first because he wanted the power to go back to the grid so they would know what's happening. But the other example was if a ground was used as a rod in the ground and you had lightning happening, the lightning could go through the ground, hit your ground stick, and backfeed into your system and blow up the house. Thoughts?
Okay, everybody see that? Everyone know what the AHJ is?
Authority having jurisdiction.
Yep. Okay. That means you do what they say. Even if it doesn't make sense, you do what they say. I've dealt with putting electrical things into plants and stuff like that. And yeah, it's sometimes it doesn't make sense. Like we had a system that we had gone through the UL process. We checked it all out in our facility. And it went up to Clackamas and it got put in another facility. And the rules in Portland and Clackamas are that if there's a new piece of equipment that goes into a plant, the AHJ decides what's going to happen to it. And they said, well, we have to do another inspection on it. It's like, but we already did that. It's like, doesn't matter, does it? Like, I guess not. if they want it to run, we have to approve it. Like, okay, it's your city. You're the AHJ. You have the authority.
Okay, I agree with that. I was just more thinking
it doesn't necessarily make sense. It doesn't necessarily make sense. I agree with you. It doesn't necessarily make sense.
Makes sense.
It doesn't necessarily make sense. That makes sense.
Yeah.
But if that's what they said, then that's what you got to do. Yeah.
I got a question for you. Can you talk to the cloud platforms? Does that provide a place where ham radio licensed people can go and use cloud applications rather than having their own equipment?
That is a really good question. So not necessarily cloud-based, but internet-based. And I have to admit, it's a lot of fun to build your own stuff, right? But you might not have room. And so what ends up happening is that there is, and let's see if I can pull it up. And I am not a user of this, but I know a lot of people who do. If you have a general class license or higher, and you have, notice what this says, you can do subscriptions for it. You can sign up and basically run somebody else's station over the internet.
But you have to be a general.
Well, it depends on where you're operating. I know a lot of them. Okay, if you're doing, for instance, repeater work, right? There's something called Echolink, and we're going to get to voice over IP. Echolink is free to anybody with a ham license, and you can basically use it. It's an internet radio hybridization that allows you to use a handset, an iPad, a computer, or whatever, to access repeaters all over the world. You do not, and because you don't have a radio in your hand, it doesn't require a radio. I mean, a radio is a cheap thing now. I mean, you can get a Baofeng for $20 and it gets you local communications. But if you want to, connect it to the internet, then you can, if you have a ham license, sign up for an Echolink account. build an all-star node or whatever, and do voice over internet protocol and pop up on a repeater somewhere else. We have people who check into our local club repeater weekly that way. When I travel overseas or anywhere else in the country and I want to check into our local, yep, Bill's got it. He's got it open. That's Echolink. I have the same thing.
This also has my my work frequencies in it too, so I can be on vacation, and if the guys need me, I can get on the radio and help dispatch and do all that stuff. When we had the issue with the weather, until the internet went out, I was able to dispatch from my phone.
Mm-hmm.
When the internet went out, I went up to my radio set up here in my house and basically dispatch, which is like, well, my job was like 30-ish miles away. Dispatch was here in my house because I had power and I had internet, so I was able to run it from here. So,
yep. And sounds like you got a noisy house today. But yeah, there's lots of hybridization. I mean, a lot of hams are really technically savvy, and so there's also something that we do called rig in a box, or RIB, where there's let's say a group of people goes to an island that has no permanent population, and they bring along a rover full of equipment, and it's got a Starlink node on it or something, or some other satellite connection. And what it allows people to do is operate that station from anywhere in the world, as if they were sitting there on that remote island that only allows 2 people to be on it at any given time. So there's and there's like contests that we do, which are competitions where we've got, and actually one of my friends up in Alaska has a massive contest station, but Alaska's only 550,000 people and really, really big. And so he's got a small group of really hardcore contesters up there, but they can't all be active all the time for every contest that goes on. Again, really competitive people. He has an internet-based station where other people who want to participate can essentially use that equipment as though they were in Alaska. They might be in Florida, a little bit different, right? But using the internet connection, so long as the internet is solid, they can operate as though they are in Alaska. So I think the last activation they had 4 operators. One was in Alaska, one was in Oregon, and a couple other guys were in Florida. So, yep. Okay, here we go. Wires, short heavy gauge wires used for DC power connections. That is to minimize voltage drop. This is a version of Ohm's law, because E equals I times R. If you have high resistance cable, what's going to happen is that you lose voltage in your cable that's available for the radio. What that means is when you do that, your radio doesn't function anymore. Typical rating for a typical 50-watt output mobile transceiver. Well, to generate 50 watts of RF, you need to input about 100 watts of power into that transceiver, because the efficiency of a transmitter is typically only about 50 watts or 50%. So if that's true, to make 50 watts, you need 100, which means if you do P equals IE, you will find that nobody uses 24 volts, so it's 13.8 volts. That's a typical power supply. And 13.8 volts at 4 amps, that's only about 50 watts, which isn't enough. So here's your minimum. A computer radio interface for digital mode operation. Okay, essentially what this is doing is when you go to connect a radio, there are a couple of things that a radio does. Here's your radio. It has a speaker, and it has a microphone on a curly coiled cable. So there's your microphone. Okay, so this is your line in, and this is your output, which is your speaker. So this is your mic, and this is your speaker. And you also have to have some way to transmit, switch it from receive to transmit. That's the PTT, or push to talk button. So when you are connecting a computer to this radio, you have to have something in your computer that will duplicate these functions. So your microphone in, you have a line out connection. To your speaker out, you have a line in connection. And you have a relay or something that controls PTT. You need those three signals to make a computer be able to control a radio at minimum. Okay. So notice audio input, audio output of a computer. It always comes down to that. Line in, line out. They might be called different things, but they're all the same. Okay, what do you use on it? What do you use to cure distorted audio caused by RF current on a shield of a microphone cable? We talked about this. Notice that there's that ferrite choke. So what we're going to be talking about here is, okay. What I'm going to bring up is I'm going to stop that share and bring up a different share. Okay. So a ferrite, notice what this says. There are two basic ferrite material groups, permeability and initial permeabilities, et cetera, et cetera. Notice that we have mix 43, 52, 61, 35, 31, 71, 73, 75, et cetera, et cetera. They're all made of manganese and zinc and iron and stuff like that. The way that these are made is that you take powdered metal, and they're typically ferromagnetic materials, which have a high permeability, such as iron and magnesium and zinc and nickel. And notice that depending on the recipe you follow, they have RFI, EMI, common mode suppression range. These are frequencies at which they really behave well. Notice you also have tuned circuits. So you want to make an inductor, you pick these particular materials on the left-hand side to operate at certain frequency ranges. You want to make a wideband transformer? What would you make a transformer for? Come on, who had the end-fed half wave?
Oh, no.
There you go. Wideband transformer. That would be the core of your end-fed half wave. So you pick the frequencies that you want to operate in, and that determines what your toroid mix is. Essentially, it's metal powder plus glue baked in an oven. And look at that. What do you notice is over there on the left side? It's a schematic of, got a capacitor, got an inductor, and a couple of
capacitor.
Yeah, what do you know? There's our old friends, and these are frequency charts that show what the suppression and what the frequency response of different materials is. This is a whole science, and they find great application because sometimes they can act as transformers, and sometimes they can act as RF suppressors, just like the one that you use on your computer power supply every day. Okay. And they're not that expensive either, which is kind of nice. Okay, which of the following conductors is preferred for bonding at RF? That would be flat copper strap. Okay, so what we're going to talk about is grounding and bonding right now, and the difference between grounds. Okay, so what is ground once again, everybody? What does it mean?
Back to zero.
That is our zero voltage reference, right? Okay, so any wire is what? What is any piece of wire?
Antenna.
It's an antenna. Okay, any piece of wire is an antenna. Okay, so if we have any piece of wire being an antenna, and we have 60 hertz, 60 hertz is our line voltage. This has a wavelength of 5 million meters, which means that practically speaking, any wire that we have in our home is going to be a lot shorter than that, which means that essentially ground over here at the bottom is going to be basically the same as ground over here, is going to be the same as ground over here. So long as it's connected in one place, it's going to be fine. For power, the key is for power, which is 60 hertz. But now we're going to mix this up a little bit. Let's say that we're doing RF and we are operating on the 20 meter band. That has a wavelength of 66 feet. And we have house wiring and we are grounded. But to get from one point in our home all the way up to this other room is 175 feet, which is not unreasonable for a home, right? Because for power, ground is ground. Does everyone agree with that?
Yeah.
Ground is ground. We just showed that. Well, over here, I'm going to put a radio. And I'm going to ground the chassis right there. Right? I have connected the power, the chassis of the radio to the ground wire that is provided in the wall of the house. Where is my actual ground?
Outside at the bottom.
Outside, yes. And it's going to be right here. Okay. How long of a piece of wire do I have between that point and my antenna and my station? 175 feet. How long is a wavelength at the frequency that I am using?
66.
66 feet. Could I not? The only thing I have to do is start here with an antenna and start drawing waves on my wire.
Yep.
Okay, so if that's my current, and I could also do voltage. Right, this is not exact, but let's say I have this. What's my voltage at my radio? Is it 0 like ground should be?
No.
No, it is not. Because ground is not equal to ground. There is power ground and there is RF ground, and they are two different things because of the different wavelengths that we are using. Power has a 5,000 kilometer wavelength. We don't care. RF, any piece of wire can function as a, well, but it's connected to ground. Yes, but it's connected to ground, but it's far enough away that you can still have standing waves on there. It can transmit. It can also receive. So where do you want to put your ground for your equipment?
It's the radio.
You want to put it as close to the equipment as you can. Even if you have a power circuit ground, you want to put a separate ground rod as close to it as you can. Because this might only be 20 feet. And if that's only 20 feet long, that's a lot safer. And you're not going to get an RF shock by leaning up against your radio like I did when I was a kid, which I did. I remember it very well.
You kissed the mic.
I did. I kissed the microphone and I got a nasty shock right on my lip. Yep. Okay. The other reason that we use flat copper strap is because of something called the skin effect. The skin effect is the tendency of radio frequency energy to travel on the outside of a conductor. So if I have, let's say, a cross section of a piece of wire that looks like this, DC has 0 frequency. It will basically permeate the entire piece of wire. AC, the higher the frequency we go, the higher the current is on the outside. You'll have 0 in the center, and you'll have most of it flowing right near the surface. The higher the frequency goes, the more pronounced the effect becomes, and that's called the skin effect. So if we have a certain amount of wire available to us, a certain amount of copper, what is the way to maximize our surface area using a certain amount of copper?
Flattening.
We pound it flat. And that's why we use copper strap for grounding. Because it's
Does that
RF
also make
ground.
it a better antenna?
It could, yeah. But it's a little harder to deal with. You know, round wire is a lot easier to deal with if it's up in the wind and between trees and stuff. It's probably
I mean, subjected to RF signal interference better because it's flat.
Possibly. It's gonna have
Platinum two?
it's gonna have probably have a it's probably gonna have a better bandwidth actually. So
Will
it's
flat tube work?
I don't know. I'd say try it. Tell us how it goes. That's part of the experimentation. Where should the negative power return of a mobile transceiver be connected in a vehicle? At the 12-volt battery chassis ground. The reason being that your car is a grounded frame. Everything is welded together, but you don't know how good of a job they did. And if you're using a 22-volt power supply coming out of your battery, essentially, and you're trying to return 22 amps, sorry, 22 amp power supply coming out of your battery, and you're trying to return 22 amps through the chassis of the car, you don't know how good of a ground system you really have. The best ground system that you have is a big fat wire that goes back to the battery.
God.
Yeah.
Does the like uh flat cable mean that like theoretically that tape measure antenna that you showed us at South is more efficient than the one that we bought that was like round wires?
Possibly. I never really thought of it that way, but yeah, it's possible. I mean, it might have it might have a wider bandwidth as well. The SWR would be better over a wider range, probably.
Okay.
That's a really good question. I've never even thought of that. See why I like teaching? How do you determine the length of time that equipment can be powered from a battery? Well, you have something called an amp hour rating. When you get a battery, it's either measured in amp hours or watt hours. That's literally amps times hours. If I have a 12 amp hour battery, that is 12 amps for 1 hour or 1 amp for 12 hours. Usually it's going to follow the, 1/10 of maximum rating per hour or something. But essentially you multiply the two together. Now, if I have watt hours, a watt, because P is equal to I times E, that involves the voltage. So if I have a 12-volt battery that's rated at 12 amp hours, that would actually be 144 watt hours. Some manufacturers like to do that. I don't particularly appreciate it. I think it's a lot easier to just talk about amp hours. Most batteries will be rated in amp hours. Operating controls. Okay. Excessive microphone gain on SSB transmissions. Can everybody hear me okay?
Overmodulated.
I'm overmodulating, right? It gets distorted. Okay. That's what happens when you have excessive microphone gain. Most handheld radios do not have a microphone gain control. However, you can control the audio going in by doing what?
Talk louder.
Talk louder or
how far away you place the radio.
How far away you place it. Yep. Some microphones are tuned really hot, and then you would basically just back off or just, talk a little quieter.
Not a Baofeng. Is there a way of making the gain on a Baofeng better?
Nope. You just either yell into the mic or back off or move it away from you. Yeah, virtually no handheld radios have microphone gains. They're all factory set. Tuning an FM receiver above or below a signal's frequency will cause distortion. Other things that'll cause distortion, if your battery is weak, if you're in a bad spot, if you have multipath, like your signal gets there from two different places at two different times. How do you control a frequency? You've got a knob on top of the radio. This allows you to change the frequency. Most handheld radios also have this, which is a keypad. This actually serves two purposes. Number one, you can punch in a frequency directly. Number two, once you're transmitting, it allows you to send DTMF, which is dual tone multi-frequency, which those of us who are older know as touch tones. So why would you ever want to send touch tones? And that's because certain repeater systems actually have functions that are accessible from touch tones. We actually used to have on our repeater when I was in college a touch tone accessible telephone line in the 1980s where we could actually punch in a bunch of codes and you'd get a dial tone, which you could then use to call a friend or order a pizza. That's called an auto patch. Most repeater systems don't bother with that anymore because phones are everywhere. But that's why they will actually transmit touch tones.
We still use it pretty significantly in the utility industry, Scott. So
there you go.
All of our systems are segregated, and you patch in with touch tone.
Yep. The scanning function of an FM transceiver, when you scan, it basically goes through a whole bunch of frequencies really fast, and it stops if it hears anything. I typically will leave my radio scanning. The purpose of a squelch. Okay, squelch is this. We're going to unshare this and hope that I remember to leave that open. I hope I did. And it's right here. And there it is. Okay, so I'm going to... Can everybody hear that?
Yes.
Yeah.
There's squelch. That's what squelch does. It basically mutes the receiver when there's nothing to listen to. If there's something there, for instance, come on. And notice when it stopped, it went away. That's the point of squelch. Now, if you're trying to hear somebody who you know is weak in the first place, you would want to turn your squelch off because the squelch, if they're really weak, will prevent you from hearing them in the first place. Okay, repeater offset. So now we're into repeater building and repeater usage. All right, so in order to explain what repeaters do, what we're going to do is draw a repeater system. There's a transmitter and a receiver. And by the way, we have a little over an hour and a half left, so I am going to do my best to make it on time, just letting you know. Okay, so here's a controller. Okay, so each one of these is connected to an antenna. Sometimes they can be connected to the same antenna, but for this case, we're not going to have them connected to the same antenna. All right, so what happens is the repeater will transmit its identification in Morse code on an advertised frequency. So I'm going to pick my own 146.72. I'm the trustee of this repeater. If I am listening for this repeater, I will be down here and I will be listening on 146.72 megahertz. The repeater will also be listening for signals coming in on 146.12 megahertz. This is known as an offset. Notice that it's 600 kilohertz lower. The offset is known as negative 600 kilohertz, which is typical for the 2-meter band. 600 kilohertz down. It could also be 600 kilohertz up, depending on what the repeater frequency is. That's called the offset. So what will happen is, if I desire to be heard by this repeater, I will change my transmit frequency so that I am now transmitting on 146.12 megahertz, so that that signal will reach the receiver. At that point, what the receiver is hearing will be sent to the controller and evaluated for whether or not it's valid. One of the things that's looked for is whether or not there's something called a CTCSS, which is a continuous tone carrier squelch system, tone, or a DCS, which is a digital coded squelch sequence. If I meet whichever of those is being asked for with my signal, then the receiver will forward the signal that I have sent, the demodulated signal, to the controller, which will then forward it to the transmitter, and it gets transmitted on a different frequency. Again, transmitter is always transmitting on 146.72, and always everything's being received on 146.12. So I continually change my operating frequency based on the published offset and frequencies of the repeater, and I have to program in my tone and my DCS if they apply to make sure that my signal is accepted by the receiver. So now you may notice also that 146.12 and 146.72 are actually pretty close to each other frequency-wise. If they are in the same band, those are really close to each other. So how do you think I would keep one frequency from affecting the other one? Because if I were to transmit and a little bit of power got back into the receiver, what would happen?
Feedback.
Distorted.
I'd get feedback and the repeater system would lock up. So I somehow have to protect the repeater system from that ever happening. What would I do? How would I do that? I could use physical spacing, right? I could put them miles apart, but typically you don't have access to two different sites miles apart. So what would I do?
Use a trap.
Yeah. Well, what's a trap?
Choke.
I mean, these are really close together frequency wise. So I'm going to show you guys something.
Doesn't a duplexer do that? It separates
Yes.
them.
Okay, so here's a repeater duplexer. This is not a cheap duplexer. Okay, here we go. Like a telewave repeater duplexer. This is what we would typically use. Those are actually cavity filters. They are really, really tightly tuned filters that essentially have a very narrow pass band or a very narrow band reject that allows two different frequencies to potentially even utilize the same antenna, even if they're really close together. These filters, that's actually basically that's a tuned cavity. That little screw up top actually moves a plunger, which changes how far down and how far down the top of the cavity is and what the tuned frequency becomes. It's very, very, very touchy to tune, but it's also very important for repeater building. And notice it's also over for almost $4,000 for a set of them, which is why a lot of individuals don't build their own repeaters. Typically, they're built as clubs because a lot of these components are really expensive. The pass band for something like this, okay, so you've got filters. This is called a low pass, and this is a high pass. The intersection of the two, because that's a band, that would be called a band pass. I could also build them so that my low pass looked like this. I could put them together. And I could say if it meets either one, well, there's a gap in there. That's called a band reject or a notch because it's a missing place. So by tuning these different repeater cavities, I can achieve up to 110 decibels of isolation between the two. All right, what's 110 decibels? How many zeros? It's one with how many zeros?
11 zeros.
Yeah. So it's that much power from one side gets through to the other one. It's a pretty good filter, right? And that's what's at the core of making a repeater that has a close offset work properly. Okay, digital hotspot. A digital hotspot is a box that connects digital voice or data system to the internet. Again, there's a lot of hybridization between radio and the internet now because we can do that. There's also a lot of stuff called VoIP, which is voice over internet. Most telephones today use voice over internet for wired phones. Even cell phones use voice over internet. We do voice over internet as well. When we get onto our Echolink system or our All-Star system, we're doing voice over internet, which then pops up on the other end and gets out on the radio. A talk group, if you're using digital mobile radio, this is programming your radio with a group ID or code. Now, one thing that's interesting about this is that if you're on a local repeater system, you have, let's say, a channel that you're operating on. And here's signal going in, here's a controller, and signal going out. You're all operating on one frequency. So anybody anywhere will be operating on one frequency at one time. And that's all there is. If you're using digital mobile radio, you have channel A and channel B, which are time shared, so that you'll have two different groups. These are actually known as color codes. And you have to pick the one that you're operating on. They're also known as talk groups. Well, one of the other things that can happen is that each of these, because it is essentially a digital system, can connect to another system somewhere, which has a receiver and a transmitter. And these systems, because they are linked together, I'll do another one up here too, can almost seamlessly and very quickly combine signals from one with other ones over the internet, so that you can have people who are in this red group transmitting here or transmitting here, and all of the red signals are sent out over here and here and here, and you can have the brown group transmitting at this one and this one. And these can be thousands of miles apart, all working together seamlessly. And this is how the whole voice over internet protocol works. This is how digital mobile radio works, and allows people who are physically distant from each other to use the internet to talk as though they were on the same repeater. We actually have in our volunteer examiners group with the Anchorage Club, we have people who are in different parts of the country who are operating in the same testing group, who get on a particular channel and all talk to each other over the radio using DMR. It's really kind of an amazing thing, because everybody can hear everybody and it's relatively seamless, and there's no bleed over if the network is operating fast enough, which it usually is. Just taking advantage of fast internet connections. Okay, a code plug is basically accessing information for repeaters and talk groups. The most recent code plug that I saw had over 200,000 different repeaters in it around the world. That's the most recent one I saw, and it's growing every day. A digital voice transceiver, you enter the group's ID code. The color code, again, you have to match the repeater color code to get into it. D-Star, this is digital communications, which is similar to DMR, but just like if you remember the VHS and Beta Wars, there's D-Star and there's DMR. There's also something called Fusion, which was developed by Yaesu. D-Star was developed by ICOM. DMR is more of an open standard. They all exist. They all do largely the same thing, with the exception of D-Star. You have to plug your call sign into your radio, because it's sent along with the packets that you're sending, because everything is digital. Okay, multiple bandwidth receive choices. On a multi-mode transceiver, we were listening to our web SDR. And the nice thing about that is that we can, assuming I can open it. So let's listen to this one. Okay, so let me ask, what happens if I do this and I find one that doesn't want to stop talking? And I do this, and I make the bandwidth really narrow.
You lose fidelity.
You lose fidelity because we're missing a big part of the signal, right? It allows us to reduce interference, but we lose part of the signal. But what if I'm using that same receiver to listen over here? It's a very narrow bandwidth, so what can I do with the filter?
Reduce it.
So what if there's an adjacent signal, a big one, really right next to it? I can filter it out. So that's why it's important to have receivers that have multiple different receive bandwidths, because you can filter out the things you don't want to listen to. So appropriate filters for certain modes. Morse code, 500 hertz filter. Single sideband, even though it's a 3000 hertz wide or 3 kilohertz wide signal, 2400 hertz is appropriate for it. The other thing we have is called a receiver incremental tuning, or a clarifier. That's more of a Yaesu term. Yaesu is another one of those 3 big companies that makes a lot of equipment. Receiver incremental tuning allows you to tune the receiver without changing the transceiver, without changing the transmit frequency. The reason you would want to do that is because if you're listening to somebody and they are off frequency as far as you're concerned, but you're on frequency as far as they're concerned, if you change your frequency, then you'll be off frequency. So you don't want to do that. To avoid that happening, you just modify the RIT frequency. PTT, again, switches the transceiver to transmit when grounded. It means push to talk. All right, station equipment. A transceiver, a portmanteau of the 2 words transmitter and receiver, they mush together to make transceiver. A device that takes RF input and output and moves it to another band. Instead of a transceiver, it's a converter. That's called a transverter. The reason that we might use some of these things is because there are bands, for instance, 900 megahertz, where we have access, but there's very little commercial equipment made for it that we can use. So we build ourselves a transverter, which takes one frequency and shifts it to another one by the use of something called a mixer, which is a frequency changer. It takes 2 frequencies and produces sum and difference and generates a new frequency. All right, power output. How do we bump it up? Well, we're talking about radio frequency. We use an RF power amplifier to increase it. So we also talked about, remember way back when, I think it was yesterday, when we were talking about transistors, and we have transistors that have 3 different modes of operation, and we have cutoff. Does everybody remember this?
Yeah.
And we have saturation, and we have this linear mode. If we're doing single sideband, things that require fidelity, we want to be using this mode, because our voice otherwise will become distorted. If we saturate the transmitter or go into cutoff, we're not linear anymore. So one time, would you actually be okay with that? If you're doing Morse code, because it's just on or off. And FM, it doesn't matter because you're just running full power all the time. And that's why you will have amplifiers that have a switch. It turns out that this up here is more efficient. And this is less efficient, which is why there's a switch. You get to choose. Okay. All right. Which term describes the ability of a receiver to detect the presence of a signal? All right. Who can whisper? I need somebody who can whisper.
Sensitivity.
Okay, that would be sensitivity. That's excellent. My ears were sensitive enough to hear it. If you whispered quieter, we might start to drop off people whose ears aren't as sensitive. That's called sensitivity. Okay, now on the count of three, I want everybody to unmute themselves. Right? Everyone unmute yourself, but then prepare to mute yourself again. Ready? On the count of three. On the count of three, say your name. One, two, three.
Seven.
Okay. All right, everybody mute yourselves again. Okay. So that is known as a pile up, right? That happens on the air all the time. That's known as a pile up. Selectivity is the ability to pick one out of that whole mess. A receiver has selectivity by being able to filter other things out. Your ears have selectivity by being able to listen to just one signal out of a whole bunch. That's known as selectivity. Again, there's something called a pile up where everybody's trying to call you at once. It gets really hard sometimes. Okay, an RF preamplifier. Typically, a preamplifier is going to be installed between the antenna and the receiver. Typically, if you can, you're going to install this all the way at the antenna. Why would you want to install a preamplifier all the way at the antenna? This comes down to signal and system development and building a system that works properly. So let's say I have a receiver right here. The receiver has a minimum discernible signal of minus 120 dBm. That means it can hear any signal that's minus 120 dBm or louder. So minus 119 would be fine. Minus 121 would be no. So what we're going to do is we're going to have this antenna up here, and we're going to bless this antenna with 0 dB gain. It has no gain. We have a signal coming in that the antenna hears at negative 119 dBm. We come down here, we have, let's say, 5 decibels of loss. What is the strength of the signal that gets down to the bottom?
Minus 124.
Minus 124. Okay. Will we hear anything? Yes or no?
No.
We will not. Okay. What if we were to put a preamplifier, which is basically a receive booster, which has 10 dB of gain right here, but it has a minimum discernible signal of minus 123 dBm.
Be minus 113.
Well, no, it's not, because how much signal is down here? What's the signal strength? We just said
124.
124. Or is the preamplifier going to hear anything to amplify?
No.
Nope. So we still don't hear anything. So what we're going to do instead is we're going to take this preamplifier and we're going to put it at the top. This has a boost of 10 dB. So what is the signal strength right here after that?
109.
Yeah, minus 109. And this could hear everything down to minus 123. So we're okay there. And now we're at minus 109. Now we're at minus 114 here. Do we hear the signal?
Yep.
Yes.
Yep. So very important to determine where you're going to put a preamplifier. This is why when cable TV systems get built, this is why they put preamplifiers all the way out at the cable box and not right at your house, because you can't amplify what you can't hear in the first place. See why DBs are so important? They're so easy to work with. Okay, a device that converts one signal from one frequency to another is called a mixer. A circuit that generates a signal at a specific frequency is an oscillator. It makes a sine wave at a given frequency. Combining speech with an RF signal is known as modulation. And we've talked about that. Okay, here we go. Signals, cures, causes of common transmitter and receiver problems. Okay, most things that you see here are going to be interference caused by either talking too loud or interference from other things. That's basically what we're talking about. So if I am operating at 10 megahertz there is something called a harmonic. A harmonic is an integer multiple of a frequency. So if my primary signal is at 10 megahertz, that's known as the fundamental, what would the first harmonic be? How many megahertz?
20.
20. Yep. Okay. What would the next harmonic be?
30.
Right. And the next one?
40.
And
et cetera, et cetera.
et cetera, et cetera. Well, okay. If you build a transmitter, you will expect to see harmonics. It just goes along with it, the way things are. How do you think the size of these harmonics are specified? This is the fundamental. How do you think they're specified? In permissible amounts of energy. dB of suppression. In other words, they have to be a certain number of dB, which is why we're doing a class, because you can build your own stuff. You have to know that at least this stuff exists. There are requirements for how many decibels below the fundamental frequency those are allowed to be. So if they say that it has to be at least 50 dB down, 50 dB down is 1,1,0,0,0,0, so 1/100,000th of the power. That's why decibels are so important. And these are harmonics. Then there are also other frequencies which just show up. Not really sure why. It's something to do with how you built the transmitter. These are called spurious emissions. So we have harmonics and we have spurious emissions. And how do you think spurious emissions are specified as far as how loud they can be?
dBs?
Decibels down from the fundamental. Exactly. Everything is specified in decibels. This is actually in the FCC rules whenever a piece of equipment is designed or accepted or type accepted for use on a frequency. It has to go through spectral analysis, and everything is put on a spectrum analyzer and shown that all the other emissions that are not supposed to be there are a certain number of decibels below the fundamental frequency that's being transmitted. How do we achieve it?
Don't buy a Baofeng?
Some of them work. Filters. And what's at the base? What is the basis of filtering?
Choke.
Capacitors and
inductors.
Yep. And if you open up any radio, what you will find is a series of capacitors and inductors building a bandpass filter that filters the output so that it allows the desired frequency to get out and reduces all the other ones. That is at the core of every transmitter. And if you have a transmitter that operates on multiple different frequencies, guess what you have?
Multiple different bandpass filters.
You have multiple different bandpass filters running it. Exactly. And they get switched in and out depending on the frequency you're on. Very good. Okay, here we go. What can cause radio frequency interference? Fundamental overload, just too much signal, harmonics, and spurious emissions. We just covered all of those. If your neighbor says that you're interfering with their TV or radio, first thing you do, make sure your equipment is not interfering with your own TV or radio. If it's not interfering with with your own, then maybe there's something wrong over on the other side of the street. If you have non-fiber optic cable TV, in other words, a cable, the first thing you do is make sure all your connectors are installed properly, nice and tight. They loosen over time, even if no one touches them. An AM or FM radio, why would it ever receive a ham radio signal? Well, I know for a fact that anytime I used to drive by a particular radio station near where I lived, if I was within 500 feet of it, it didn't matter where I was tuned. I would hear that radio station. And it was operating legally, and I was operating legally. The reason being that there was just so much signal there that it swamped my radio's ability to do anything. So if it's a ham radio, I would receive it also. My receiver was unable to reject strong signals. There was just too much stuff. How can you protect that? Yeah, there's that word again. Everybody, get used to seeing that word. Filter, 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 filter. Everything, almost everything is corrected by filtering, because filters are the basis of frequency selective things. Filter, filter, filter. How do you reduce overload of a VHF transceiver? What do you do?
Filter.
A band reject filter. Well, you build a filter that rejects a certain frequency so you don't get swamped. And okay, what do you do if something in your neighbor's home is causing harmful interference? Okay, so there is something that we all need to get used to seeing, and you may or may not have ever seen this before, which is Part 97. Part 97 is the amateur rules. This is the amateur radio rules. There's also Part 95, which is citizens band, and Part 90, which is commercial band radios. And all of those basically specify what radios are and how they have to behave. These are all licensed services. However, there's another one, which is called Part 15. Does anyone know what Part 15 is of the FCC rules? This covers unlicensed and unintentional radiators. Part 15 is what governs your computer power supply. Part 15 is what governs your computer. Part 15 is what governs the clock on the wall. Part 15 is what governs your television. Basically, unlicensed, unintentional radiators that may emit a signal. So if there's a question between, let's say, a licensed service, let's say Part 97, which is an amateur license with amateur equipment, and Part 15, which is unlicensed stuff, if there's a debate between whose fault it is, who is at fault?
Part 15.
Part 15 is always going to be at fault. If you have a, like I do in our house, if you have a one of those really cool dimmable multicolor LED light strips, and every time you turn it on, you get interference on your ham bands, whose fault is it?
15.
Part 15. That's right. It's the lights. If whenever I transmit on my ham radio, which is a licensed transmitter that is deemed to be operating properly, and these lights start to flicker, whose fault is it?
97.
Nope. I'm legal. My stuff is operating legally. Whose fault is it?
Part 15.
It will always be part
15.
15.
Part 15. Yes, it'll always be part 15. If you are interfering with your neighbor's television, you may want to help them. But if you can show that there's something about their television that does not work properly, it cannot reject legally transmitted signals. It is their fault and not yours. That doesn't mean you shouldn't help them. One way you could help them is you might install a filter on your stuff to keep your frequencies away from them. You might also install a filter on their stuff to keep your frequencies away from them. Filter, filter, filter. Filters are the cure for a lot of different things. Does anybody remember having a telephone plugged into their wall that they rented from the phone company?
Yeah.
And mine was
Okay.
attached to them.
So what happened if there was a ham down the block and they were operating legally? What would the phone company do?
They put a filter at your house.
They'd come out and they'd put a filter on your phone. That's right. They would actually come out to your house and put a filter on the phone. Okay, if your audio signal through an FM repeater is distorted or unintelligible, your transmitter is either off frequency, your batteries are low, and your signal is not being transmitted properly, or in a bad spot, A bad spot, again, is you're in a valley or you have multipath or any number of different things. RF feedback in a transceiver means you're going to sound unintelligible. What could you do if your handheld mobile transceiver is over deviating? Over deviating is when your signal on FM gets too wide. In other words, it takes up too much bandwidth. If it takes up too much bandwidth, the reason it's taking up too much bandwidth is that you're basically too loud. You're causing it to spread too far. What you do is you talk further away. All right, basic test instruments and soldering. All right, let's just start by saying, who here owns a Harbor Freight free voltmeter? Raise your hand if you've ever gone to Harbor Freight and gotten one for free. Yes, I love my Harbor Freight voltmeter because it costs me absolutely nothing. Sometimes I just give them away. And well, the thing about Harbor Freight is that if you look at their voltmeters, which are great for a certain task, okay, let me pull one up. Okay, so here's our Harbor Freight 7-function digital multimeter. Okay, everybody see this beautiful Harbor Freight 7-function digital multimeter? It was $7 and now it's $4.89. And sometimes if you have the right coupon, they'll give it to you for free. Okay, this is a digital multimeter. It actually does a lot of things. It's got leads. It can measure capacitors. It can measure transistors, I think. Yep, transistor checker down here at the bottom, NPN, PNP. It can measure current. It can measure amperes. It can measure resistance. So it's a true multimeter. Now, I could also take a look at this multimeter, which is what I use at work. Here's my Fluke 87. Okay, notice how much my Fluke 87 cost me. Everybody see that price? Where'd it go? There we go, $503.49. Well, we look at what it measures. It measures volts, it measures ohms, it measures temperature, it measures amps, and a few other things. So how come this Harbor Freight multimeter, which cost me $4.89, costs $4.89, while this Fluke multimeter costs $500, when really they just measured the same thing?
It's a pretty yellow.
It's yellow, but actually it's just the case.
Tolerance.
It's easy to get the smoke out of the Harbor Freight one.
So yeah, the Harbor Freight one is rated in theory 250 volts. I would never use it to measure 250 volts ever, because it's a $5 multimeter. The other one is rated at 1,000 volts. That's what I use at work. I would actually, I'd still wear gloves, but I would actually use it and be fairly sure that it's not going to explode when I'm measuring a really high voltage. It's probably also a little more accurate, although I can't guarantee it. But basically, what you're doing is you're paying for the extra quality and security that what you're getting is what you think it is. Do I have the Harbor Freight multimeter? Yes, I throw it in my tool bag. I use it for measuring DC voltages up to 24 volts. I'll even carefully use it to measure 120 volts to make sure my power is on, stuff like that. I measure 480 volts with the Fluke all the time. It's built a lot better. So what do you use the multimeter for? Voltage and resistance, and sometimes amps as well. How do you measure electric potential? A voltmeter. When you measure voltage, you use the meter in parallel. You're trying to measure the voltage across a certain thing. So how can you damage a multimeter? Well, you can put it on the wrong setting. That's a big one. And if you think about it, how do you measure resistance? How do you measure resistance of a resistor that's just sitting there on your table?
In parallel.
So let's say you've got a resistor that's just sitting on a tabletop and it's not connected to anything.
You have to run power through it. You have
to run power through it somehow. So you hook up your meter, which is an ohm meter. Okay, well, it'll say that it is 26 ohms. How does it know that it's 26 ohms? How do you measure? What's Ohm's law?
Sure.
E equals I times R. Well, what's the thing here that you truly have no idea of what it is? You have that mystery resistor, right? So if you, right, it's a mystery resistor. So if you have a battery right here, and you have a voltmeter right here, and you know what voltage the battery is at, and you have an ammeter, which is in series, and when you connect it, you can actually measure the amount of current accurately. If you're measuring volts and amps, what does that mean that you can then know?
You know what the resistance is.
Then you know the resistance. So this complex calculation is being done with two separate meters inside your voltmeter. It has to have a battery inside the voltmeter, so it has to have power. It uses that to measure current and voltage. So what happens if there is another battery already hooked up to your resistor in a circuit? When you're trying to measure, well, what's going to happen? You're going to get extra current flow, and maybe it comes up and it goes into here and it goes through your ammeter like that. What's going to happen to your meter?
You could cook it. Sure.
You're going to let the smoke out of your meter. That's right. Which is why it's very important to make sure that when you have a device under test, like a resistor, it is completely separated from the circuit that it is located in. Because an ohm meter for measuring resistance is a completely self-contained device with 2 meters in it. Okay, high voltages. If you're measuring high voltages, let somebody else do it. That's what I do. I let somebody else do it. But
how high is high voltage?
Anything over 100, anything over, well, technically anything over 50 volts is high voltage. Realistically, I'll measure up to 480 volts, but you have to be suited up to do it properly.
Holy smokes, that's dangerous.
So I need to go, you need to go find somebody who's got the right clothing and got the right gear. If you're in an industrial situation. If you've got 240 volts in your house, you know, I'll still do that and make sure it's okay. That's about as high as I really want to go. You have to make sure that the voltmeter and leads are rated properly. To measure resistance, you do it in parallel like we just drew. You have to make sure the circuit's not powered or you'll blow your meter up. If you find that an ohm meter has resistance that starts at 0 and goes up to infinity, that means that you're basically charging a capacitor instead of looking at a resistor. And you could even try that. Just make sure you discharge your capacitor carefully. To measure electric current, that's amps, so we use an ammeter. To measure current, we connect it in series, unless you're measuring a lot of current, in which case your meter typically won't be able to handle it. At that point, you then get something called a clamp-on ammeter, which is an inductive ammeter that looks at the magnetic field that is circling around the wire and measures the magnetic field. Do not use acid core solder. We typically use a rosin core. That's a cleaning agent. Acid will destroy your circuit board, so don't use acid. A solder joint, when you heat it properly, should be nice and clean and shiny. Okay. Here we go. Most technicians use an FM transceiver for their first amateur radio. I still use mine every day. A repeater station retransmits it. There are other stations that are allowed to retransmit automatically. Repeater, auxiliary, or space station. An auxiliary station is like a store and forward or just a forwarding station. It just repeats anything it hears and forwards it down the chain. That could be like on a mountaintop, a microwave link, something like that. A repeater station, again, is something that repeats what it hears and retransmits it. A space station is anything 50 kilometers or higher orbiting Earth. That is the definition of a space station. And I guess it really doesn't have to be orbiting. If you got a high enough rocket, it could technically be in a space station, but it would have to get 50 kilometers up. It's a pretty good sized rocket. A linked repeater network. we actually have one in Oregon. We have 50 something repeaters that are connected together so that if you access one repeater, you access all the repeaters. That's a linked network. 2-meter band, the offset is plus or minus 600 megahertz, 600 kilohertz. The 70 centimeter band, you just have to memorize that it's plus or minus 5 megahertz. Yep.
You have probably explained this a multitude of times and ways, but I have not yet to figure it out. If I am transmitting from a Gardner Mountain repeater, it goes through Lane and 2 others. How does it know to pick up those signals and transmit them so they come out in Roseburg?
That's automatic.
How?
By virtue of the fact that those repeaters are part of a linked system, there's a permanent backbone that exists on a totally different frequency that shares signals between them. That could be over the internet. That could be over an RF link. The entire Peak Radio Association system with its 50 plus repeaters uses a combination of permanent RF links over microwaves and VHF and UHF, as well as internet connections to connect all the repeaters together. They're always listening to each other.
Okay, so it also goes south like Baldy and Brookings and
everywhere it's connected, and it's automatic.
It's magic is what it is.
It is pretty cool, isn't it? But it takes a lot. It takes a lot of work to maintain something like that, which they do. They put a lot of effort into it.
Okay, thank you very much.
Yep. Okay, a subaudible tone, that is a typically anywhere between 67 and 254 hertz tone that is then stripped away out of the signal because it's subaudible. It's a lower frequency than most people can hear. If it's there, the receiver says, oh yeah, this is coming in with the right tone, and it takes the signal and retransmits it. If it's not there, it will reject it immediately. There's also something called DCS, which is digital code squelch. It's a sequence. It's a little frequency hopping sequence that has to be programmed into your transceiver so that if it's there, your signal will be accepted. If it's not there, your signal will be rejected. There could be a repeater that has both of them. How is a transceiver's reverse function used? Typically on a handheld radio, there's a little button that says REV or reverse. What that does is if you have a split or an offset programmed into your handheld, it will cause it to momentarily listen on the other frequency, which is what other people are transmitting on. And the reason you would want to do that is if somebody is transmitting on the input frequency, you want to listen to that frequency to see how loud they are and see whether they're transmitting the right signal. Distortion on voice peaks. That means you're over deviating. Again, if you're talking too loudly, you're going to be over deviating, which is going to cause your signal to get too wide. If it gets too wide, part of it will get cut off. If you cut off part of your signal, part of your voice is no longer present, which means your signal will get distorted. How do you call another station? You say their call sign and then identify with yours. KF7GGN, N7JI.
N7JI is KF7GGN. Go ahead.
There we go. We just did it. Say their call sign, then say your home. All right, KF7GGN, just wanted to see if you were awake. Thanks, Scott. N7JI clear.
F7GGN clear.
So there we go. And if I just wanted to say I was there, I would just say N7JI listening or N7JI monitoring. There's also something that we're going to do called calling CQ. Typically, we never call CQ through a repeater because that means I'm looking for somebody, anybody. But if you know there's a repeater there, your signal's getting picked up. So you're not really just like, calling out into the ether and hoping that somebody's there. You just say N7JI listening. Transmitting and receiving on the same frequency is known as simplex. Why do we use simplex? because there's
You don't want to
sometimes
tie up
that,
the repeater.
yeah, we don't want to tie up a repeater that's potentially being used by somebody else. A repeater is a resource. If nobody's using it, then it's okay to use. But if you're a half a mile apart and you're just talking to your kids or something, then there's no reason to use a repeater unless you have some expectation that somebody else is going to want to join in. 146.52 is the national simplex calling frequency on 2 meters. Virtually everybody who has a handheld or mobile radio will program that frequency in and scan through it. I do as well. On the 70 centimeter band, it's not used as often, but it's 446,000.
Question.
Yeah.
Let's say you reach somebody you want to talk to and you want to switch to a unused frequency. How do you go about doing that actually?
QSY.
Elaborate?
QSY means change frequency.
No, I mean, how do you pick another frequency?
It depends. You want to go simplex?
Sure.
Then you say, I'll see you over on, that's where you have to know what simplex frequencies are available. And you just say, okay, I'm going to go over to 146.56.
So just pick a random frequency that's within your license limitations and
No, because you got to know where the simplex frequencies are. Because if you did just pick one willy-nilly, you might end up somewhere on a weak signal frequency. You could end up on a satellite frequency. You could end up on a repeater input, in which case every time you transmitted, you'd be firing off someone's repeater. And they wouldn't be terribly happy about that, which is why it's important to know, what the frequency band plan is in your particular area. And in fact, there is something in Oregon, if you happen to live in Oregon, but every state has one. We have something called the Oregon Region Relay Council. And I think I have to unshare, stop share, and start here. Okay, so notice we have this, ORC. This is a frequency coordinator. In Oregon, for instance, we have this band plan. This is to keep the peace and so that people don't obliterate each other on the air. This is how repeaters are allocated. Repeater channels are allocated. Simplex frequencies. Notice we have simplex down here. 14642 to 14660, 20 kilohertz channels. That tells you where the simplex frequencies are. Same up here at 14740, 14758. So everything, the basically our band, the FCC rules say you just have to be within the band. To keep the peace and make sure you guys don't kill each other on the air, you have to understand what the band plans are in the particular area where you are. Notice also we have published coordinations. These are repeater pairs that have been applied for and assigned by the ORRC. These are all the repeaters in the state of Oregon. And they all go through coordination to make sure they don't interfere with each other. And again, every section, every state is going to have that same kind of thing.
So just search for, in my case, Washington State Amateur Radio Band Plan.
Frequency coordinator. If you look up a frequency coordinator for Washington State. Okay, what's the meaning of the procedural signal CQ? CQ means I'm calling anyone. And what should you do before calling CQ? You make sure you can be there and transmit there, because if your license doesn't permit you to transmit there, you have no point doing it. Make sure that nobody's using it, and then you physically will key the transmitter and say, is the frequency in use? Because there's a chance that somebody could be in the middle of a contact and you can't hear them because they're not talking at the time. How do you respond to someone calling CQ? You give the other station's call sign, and then you're on. When making on-air test transmissions, this is very important. You always have to identify. There cannot be an unidentified transmission made over the airwaves. Now, it has to follow the rules. The rules say You have to identify every 10 minutes and at the end of communications. So you might send 5 or 6 test transmissions and then your call sign. Very often, if I'm doing that, I just transmit my call sign over Morse code. That does both. We also use a lot of Q signals on Morse code. Some of them have found their way into voice communications as well. QRM means I'm getting man-made interference from some other station. QSY means I'd like to change frequency, or QSY over to 146.52, which means I'm going to change frequency. A band plan, we just talked about this. A voluntary guideline for using different modes or activities within an amateur band. And if 2 people show up and they want to use the same frequency, they have to negotiate it. Don't fight over it. Just figure it out. There's also something called a volunteer frequency coordinator. Again, in Oregon, we have the ORRC. That's a person or a group that has been nominated to basically adjudicate issues that come up and assign frequencies and create a band plan. And people who are repeater owners and I believe repeater owners basically elect that person to that role. Okay, now we're into public service and emergency communications. How about a 5-minute break, everyone?
Works for me.
Okay. I will be
Hey,
back.
Scott.
Yep.
I got to drop because I got to get ready for the Sabbath. I'll watch the rest via the YouTube when you send it out.
Okay. Where are you located? Oh, did he go? Oh, he went. Okay. All right, break time. All right, who's got questions?
I have a question.
Good. Let's hear it.
When you said that that Oregon website showed all the repeaters in the state, did that also show all the frequencies?
Yes. Here, I'll bring it back up. So this is the published coordinations for every repeater in the state of Oregon. Now, this is not easily searchable, and it does not necessarily show what repeaters are connected to what other repeaters. So an easier resource is this thing called Repeater Book. I can't remember my password. Doesn't matter. And what Repeater Book does is it allows you to, yes, I'm human. This allows you to, for instance, look at North America. I think I did that. Pick Oregon. Oregon 2-meter repeaters. It shows you all the repeaters in the state of Oregon on 2 meters. The other thing it does is there's one thing that I think says like show map results. Because why not, right? So this is our club repeater somewhere over here. There, it's right there. There's a repeater. That's Junction City. Shows you exactly where it is. There's another one I wanted to see that I don't think showed up on that map. Oh, wait, it's hiding. It's this one. Nope, that's not it either. It's hiding there. You can also search by call sign. So here's our club repeater. And this one used to show the coverage area. I don't know why it's not showing the coverage area now.
What's the difference between a club repeater and a normal repeater? Is it just who owns it?
Yeah. Who owns and administers it. And most repeaters are owned by clubs. And that's just because of the fact that it's a lot easier for people to get together and do it as a group. First of all, it's not cheap. I mean, I guess it doesn't have to be that expensive, but it's typically not cheap. And you need a location, which means you have to put it somewhere, which means you have to, get access to a tower or a rooftop or something. And it's easier for a group of people to maintain it and pay for it than it is for one person to do it. Which is why support your local club, everybody. Go find your local club and join your local club.
Unless your local club's a bunch of idiots.
Then form your own club. That's how new clubs form.
Myself and 2 of my buddies did a GMRS repeater.
Mm-hmm.
Now I'm trying to get them to get their ham license so we could then put up a ham repeater.
You'll have an easier time putting up a 70 centimeter repeater. It'll be a lot cheaper. 2 meters, not so cheap, but 70 centimeters, it will be easier because you have 5 megahertz offset, and there's a lot of experimental and probably widely available frequencies on 70 centimeters. 2 meters, because it's only a third the size, even less, typically fills up really fast.
Yeah.
Out of curiosity, what's the average cost on a repeater?
It varies a lot. I mean, it depends where you get you could build your own controller. You could buy a controller. Controllers probably, I'll just go out of the, I don't know, limb and say $1,000. And then you typically don't use ham radios. You would typically modify commercial radios They're designed to, well, first, they're plentiful, especially, you know, 1 or 2 generations older. And you can get them for $500, $600, you know, and make it so that they, you know, are on one frequency and will basically run 100% duty cycle, which is what you're asking from them at 25 or 50 watts. They're designed to run 100% of the time. But your antennas, your feed lines, you know, a lot of it depends where it comes from. You know, if you buy, if you end up with, you know, 1.5 inch hard line and you buy it new, what is it, $20 a foot? Maybe more. But you know, people take down systems all the time, and I've bought, you know, a 100-foot spool of 1.5 inch hard line for what, $2 a foot? It's secondhand. It's got paint all over it, but it still works. So a lot of it depends, you know, how much you want to spend and what you want to build and where you get the repeater filters from and whether you can tune them yourself or,
No,
you
I
know, you
was
have to.
just curious because I've got access to about 260 towers around the state of Michigan.
Yeah, you're luckier than most.
We
It's hard to find somebody who's willing to give you a key.
we used 2 Motorola radios that we had
Mhm.
that were taken out of patrol cars, so that saved
Yep.
us a bunch of money right there.
And they're really reliable. And
Yeah.
we've got around or this part of Oregon, we've got a lot of Kenwood TK 750s, which are, you know, commercial mobile radios. They work really well. Apparently they can still be repaired. So they do fail from time to time. I mean, it's 100% duty cycle if you're a busy repeater. They're transmitting all the time. So,
Hey,
all
Scott.
right. Yeah.
I got a quick question. I was looking at that repeaterbook.com site and I don't see my friend's repeater on there. Is there a reason why it wouldn't be on there? I just checked under amateur repeaters and I checked under GMRS.
I don't know if they're going to list all the GMRS.
Because we use it for our CERT training.
Yeah, again, I don't know if it's going to be listed.
Okay. All right.
There's a separate in the repeater book. There's a separate section for GMRS. You can find it. You just have
Yep,
to.
I did look. I looked under GMRS and
Okay.
amateur ham.
Well, part of it too is if they haven't actively gone through the process of listing it, then it may not be.
Okay.
It's not like it's not like they, you know, they poll and find them all.
It's not a mandatory thing then.
No.
Okay.
And quite often the GMRS ones are tactical repeaters that are only put online when you're training or using them, and then it's taken back offline again.
Mm-hmm. And sometimes they're private. So, you know, there is the concept of a private repeater. That does exist, you know. So,
well, we use it for official functions though, so that's why.
Yeah, so that's not so.
Yeah.
Yeah. Okay, here we go. Public service and MCOM. ARES is the Amateur Radio Emergency Service. Raise your hand if one of the reasons you're here is for emergency communications. Yeah. Okay. So MCOM. ARES is run by the American Radio Relay League. It is the Amateur Radio Emergency Service. It's a volunteer organization that is not governmental. It's run by the American Radio Relay League using equipment, licenses, and people. The other one is the Radio Amateur Civil Emergency Service. It has that word civil. That means that it has something to do with the government. You basically will register with your local jurisdiction of the government. That could be city, it could be county, state, and you become a part of RACES. The difference between ARES and RACES, there's not as many RACES groups around these days. There's a lot of ARES groups. RACES is basically for civil defense. And it's run by a government agency. ARES is not. They're essentially the same, but you register with different groups and they have slightly different purpose.
People don't trust the government.
Yeah, and also notice RACES is an FCC Part 97 service for civil defense communications during the national emergencies. So it is more official. ARES is basically a group of hams organizing to do this. RACES is actually mentioned as a governmental thing. Net control in a net. A net is short for network. It is the person who is at the center of the net who is directing the traffic, which is the information passing from person to person. The net control station holds the ball and tells people who to talk to unless there's an emergency. So typical net practice is to not say anything unless you have an emergency or net control calls on you. Traffic is all the messages that get exchanged by stations on the net. When you check into a net, you're basically saying, I'm available for use. I'm available to handle traffic if you need me to do so. Once you check into a net, you're typically expected to remain active until you either check out or somebody releases you. Good traffic handling, you pass a message exactly as received. It's very important to make sure that you don't make any mistakes. One of the things that we do to make sure that happens is we use the standard ITU phonetic alphabet. Notice it says a standard phonetic alphabet. The most common that we use in amateur radio is the ITU alphabet, Alpha Bravo Charlie Delta Echo Foxtrot. If you happen to be a police dispatcher, you may run into the fact that you have two different phonetic alphabets floating around in your head. That does happen. I know several people that happens to all the time because they do work as police dispatchers. Formal traffic message. Formal traffic is information, the preamble of a message is information needed to track the message, who it's coming from, the time it was sent, the person it's going to, etc., etc. Another thing in a radiogram is formal traffic, is the check. The check is a number of word or word count, or word or word equivalent that's in the message. I am going to the zoo. That would be a check of 6. If somebody repeated that message and they got a number 5, they'd say, wait, those don't match. The check is wrong or the message is wrong. Please repeat it. These days, there's not a lot of traffic that's being handled by voice, although it is still done. A lot of it is digital these days. When do FCC rules not apply to operation of a station? The answer is they always apply, but if these words will continually pop up, immediate safety of human life or protection of property, that means a serious immediate threat that has to be addressed and there is no other way to get through. Then you're allowed to use a station that you're not licensed to use. You're allowed to operate outside your license class, et cetera, et cetera, et cetera. So basically, if you're going to do that, you have to really be able to prove immediate safety of human life or protection of property, and there was no other way to do it. If you have a choice between using a cell phone and your cell phone works, or operating outside your license class, use your cell phone. If you're out in the woods and there's only one way to get through and you know it's an immediate threat, go ahead and, explain what happened afterwards. Who can contact the ISS on the VHF bands? If you are legal to transmit on the VHF bands, you are allowed to talk to the ISS or any other satellite orbiting overhead for that matter. That typically requires a technician class license or higher. If a satellite is operating in mode UV, that's UHF up and VHF down. Our UHF band, if we take a look at our band plan, our UHF is going to be right here. What? Oh, 9. So UHF is going to be 70 centimeters and VHF is typically going to be 2 meters. So UV. Nobody does VU, only UV. It could also be UU or VV, but typically we do UV. What mode of transmission is commonly used by satellites? Well, FM, the ISS has an FM transceiver and repeater built on board. You can also do digital communications with it. Some Some satellites actually carry a single sideband transceiver. Some also will send digital communications as well as Morse code. Um, effective radiated power, that's basically how much signal is going up to the satellite. If you are exceeding the amount necessary to be heard, some repeaters up there can actually handle multiple different signals at the same time. If you're transmitting with too much power, you could block access by other people. How do you determine if your satellite uplink power is neither too low or too high? You're basically listening for a beacon coming out of the satellite, which is indicating health, status, call sign, etc., being sent out of that satellite. And if your signal strength coming down on the downlink, you should be able to hear yourself on the downlink. If you're getting into this repeater up there, you should be able to be listening on a different frequency to yourself and be able to tell that your signal is about the same strength as the beacon. LEO, that stands for low Earth orbit. Most ham satellites, excuse me, most ham satellites do not have the funds to get up to geostationary orbit or geosynchronous orbit. Geosynchronous orbit is about 22,000 miles up. It takes a lot less rocket fuel to get up to 220 miles up than it does to get to 22,000 miles up. So most ham satellites are in are in a low Earth orbit, which means that they go a lot faster around the Earth, kind of like, the International Space Station gets a sunrise every 90 minutes or so. Ham satellites will do the same thing. They'll zip overhead and it'll take 10 minutes for a complete pass from one horizon to the next. A satellite beacon, anybody can listen to a satellite beacon, indicating what's going on with the satellite, what the temperature is, where it's located over the Earth, all the telemetry information. In order to pick up and find a satellite's orbit is determined by its Keplerian elements. If you go to a site called AMSAT, which is the Amateur Satellite Corporation, they list Keplerian elements for satellites that are up there. They also list a finder. They also have a finder where you click on a satellite and it will show you on a map exactly where the satellite is. Kind of like NASA has something called Spot the Station, except that this works for all of the 100 plus satellites that are carrying amateur radio up in space. Doppler shift. Okay, if anyone's ever heard when a fire truck is coming toward you, the pitch will be higher than it normally would be, and as it drives away, it goes lower, and that's because the sound waves are being stretched. Well, in order for that to happen and be noticeable, it has to be moving at an appreciable speed compared to the waves that are being transmitted. We don't get that on Earth typically with radio waves because we're not moving fast enough. But what happens is if you're getting a signal that's coming from space, moving at a speed of light, the satellite that is transmitting it is coming toward you and moving away from you fast enough that it actually shifts the radio frequency slightly. So you have to observe Doppler shift in order to be on the correct frequency to talk to a satellite. When it's coming toward you, you have to tune up higher. And when it's going away, you have to tune lower. And when you're transmitting to it, you have to account for the fact that the frequency is raised when it's coming toward you and lowered when it's going away. And you have to change your transmit frequency also. Spin fading. Satellites typically do not remain completely stationary in orbit. The satellite will typically rotate. Its antennas will come and will be pointed toward you and then suddenly be pointed away and then to be pointed toward you again. That causes something called spin fading as the satellite is turning in space. All right, operating activities. Contesting. Contesting involves it's one of my favorite activities on the air. It involves an adrenaline fueled rush to make as many contacts with as many different stations in as many different places in a fixed period of time as possible, which means you're basically trying to make a contact and say, all right, thanks, next. Notice send only the minimum information needed for identification and the context exchange. If the context exchange is the serial number of the contact and a signal report, it could be 599126. Thank you. Next. And then you give your call sign and somebody else answers. It's very rapid fire, very minimal information, but also for those of us who are kind of adrenaline junkies, a lot of fun. A grid locator. Okay, this is actually one of the things I believe that I sent out. A grid locator, the entire world is separated into grid rectangles, which are called grid squares. They're not really squares, they're rectangles. But the whole planet is split up into 1 by 2 degree blocks, 1 degree in latitude, 2 degrees in longitude. And within those blocks, you basically have a system by which you're given 2 letters and 2 numbers. And that grid, for instance, will be like CN84. And that will identify where you are on the entire grid that makes up the grid that covers the entire world. And so after a while, the benefit of doing so is that it more accurately identifies where you are compared to other people in your state. So let me see. I've got a grid square map. There we go. Can everybody see that?
Yep.
Okay, so here's our grid square map. Notice that CN, DN, EN, FN, CM, DM, EM, FM. These start all the way at AA and go all the way up to, I think, RR. And so within each one of these, it's then broken up into 100 smaller grid squares. So like from 00 up to 99. So again, for where I live in Oregon, it would be Charlie November 84. If somebody in Idaho were trying to talk to me and didn't know where I was, just that I said that I was in Oregon, well, am I all the way down here in the southeastern corner or all the way up here in the northwestern corner? If they're using a very, very narrow beam width antenna on UHF, for instance, they wouldn't have any idea where to point. If I told them, okay, well, they're in DN26 and I'm in CN84, they could figure out a good heading to talk to me on. So it identifies where you are a little bit more accurately than just I'm in this state. And that's known as a grid locator. Which of the following methods is used to locate sources of noise interference or jamming? That would be direction finding. We do this for that purpose. We also do it for fun. It's known as fox hunting. This is a sport in Europe where people will run around, and actually it's a sport in the United States, it's not as popular. Will run around through the woods trying to find the hidden transmitter. So it's kind of like a combination of geocaching and cross-country running. A hidden transmitter hunt, you would use a directional antenna. Yes, and it's also very useful, and as Rick points out, that kind of skill is also useful for ski patrol and other, find the hidden transmitter. It might be that somebody is an unintentional hidden transmitter, buried in a snowbank or something. IRLP, Internet Radio Linking Project. The most important thing to note is that IRLP uses VoIP, which is Voice over Internet Protocol. This is how most voice communications are done today. This is what connects telephones. This is how we are talking right now. It's voice over internet. Voice over the internet using digital techniques. In order to sign up for Echolink is a voice over internet protocol. You have to register your call sign and provide proof of license. And once you do, you are given access to the app on your phone, the app on your computer, and you can talk to people on repeaters all over the world. IRLP, how do you establish it? If you're over on a repeater that uses IRLP, DTMF, again, is touch tones. Beep, 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 beep. You punch in the right code, the repeater is then connected to the internet. And a gateway is a station that connects other stations to the internet. Okay, here we go. Rules and regs. This is the driest part of class, but it's also one of the most straightforward. All right, the FCC runs amateur radio in the United States. The rules are in Part 97 of the FCC rules. That is Part 97. And this is where we're going to start talking about specific terms. So while I'm showing this, I'm going to pull up FCC Part 97 in all its dryness. And you do not have to read all of FCC Part 97. You just need to know that it exists. And basically, if it's a rule, it's going to be in FCC Part 97. So here we go. FCC Part 97. Everything about amateur radio is contained within this service, within this part. This is actually one of the most important parts of Part 97. Right here at the beginning, basis and purpose. There are 5 reasons that we exist and are allowed to exist and are encouraged to do what we do. A, B, C, D, and E. If you ever wonder why it is that we get to use these frequencies, why we get to basically use them and not pay for them, these 5 reasons are exactly why. Right? First of all, amateur service to the public, voluntary, non-commercial communication service, particularly with respect to providing EMCOM, emergency communications. This is basically reason number 1. Non-commercial. We cannot collect any money. Provide specifically with respect to emergency communications. So we're here for preservation of safety and security and helping the public. And we don't collect money doing it. So we don't make any money. We don't spend any money. Contribution to the advancement of the radio art. Teaching people how to do this. Teaching people how to continue development. Advancing skills in the communication and technical phases of the art. This is a very technical hobby. Radio is not a simple thing. It's kind of amazing when you think about, you push the button, all the things that have to work in order for this to happen. Which is why I say again, unlike a lot of other services, we are not appliance operators. You know, you can be an appliance operator, but we are not appliance operators. We're the ones actually who are, in a lot of ways, the citizen portion of those who are at the forefront of radio and communications technology. Creating trained operators, technicians, and electronics experts. About 90% of broadcast engineers in the recent past were ham radio operators. I wonder why. And continuation and extension of the amateur's unique ability to enhance international goodwill. So we are actually allowed to talk to North Koreans if anybody there has a license, for instance. You know, country is not particularly friendly with the United States. This happened a lot back in the Soviet Union era, the Eastern Bloc. I have lots of friends. I have lots of cards that I've gotten mailed to me from people who lived in countries that we were definitely not friendly with. The Cold War was a real thing, but amateur radio is not political. You know, it's a way to establish international goodwill. Okay. Those are the 5 reasons we exist. Okay, a beacon is a one-way transmission containing information for propagation or experimental activities. A space station is anything 50 kilometers above the Earth's surface. When are you allowed to willfully interfere with another amateur station? The answer is never, even if they're really annoying you. You have a control knob for turning the dial. Get used to exercising it. If somebody is doing something that you don't like, it's sometimes just easier to spin the knob. Now, I will say that amateur radio is a largely self-policed service. If you hear something that's going on, it's okay to tell somebody else. You know, that's part of self-policing. You know, it makes us all look bad if somebody's doing something they shouldn't be. And every so often on the air, you may hear something like that. You can't talk to anyone who doesn't have a license, but you can certainly mention it to somebody. Okay. Volunteer frequency coordinator. We talked about that. Recommends transmit and receive channels and other parameters for auxiliary and repeater stations. The volunteer frequency coordinator is chosen by stations who are eligible to be repeater or auxiliary stations. Basically means I've got a repeater. I want to have some say in who chooses what. Okay, this is complete memorization of this. And that's why I sent this to everybody. This is your roadmap to all the frequencies that you can use based on, notice this E, A, G, and a star. That tells you what privileges you get for what license class. The star is novice and technician. The E is extra, A is advanced, G is general. Notice that above 50 megahertz, there is no such designation. That's because everybody with any license, except for novice, can operate on any of these frequencies up here.
Did you say except in Chicago?
No, except for novice.
Oh.
Novice, you haven't been able to get a license in like 35 years at a novice level or something like that. But there are still people who have novice licenses, because once you have it, you don't get grandfathered into anything else, and you don't upgrade automatically or anything. So, you know, so long as you keep renewing it, you keep your license. So there are still novices out there, although I don't think there are many. What frequencies in the 6-meter band? Okay, 6-meter band covers 50 to 54, and so on and so forth. There you go. So this is really just memorization of where those frequencies are. 2 meters is 144 to 148. Well, 146.52. And if you ever run into issues, you'll remember that circle with the 300 and the F and the lambda. You can always plug one in and figure out the other one. Thank you, speed of light. On what HF bands does a technician class operator have phone privileges? Phone is another fancy way of saying voice. And notice that this says novice in the little blue area, novice technician voice, down there at the lower left. Well, 10 meters, the 10-meter band has been awesome for the last year because we're at the peak of the sunspot cycle. Technicians have gotten the chance to go and operate there on a band which is not dead, which is kind of cool. For the last 9 years before that, they did not. So this is a good time to be getting into this, and a good time to practice so you can upgrade. Oh, somebody please answer that. Okay. Which of the following frequency ranges are available for phone operation by technicians? There you go. It's right there. Where can single sideband be used over 50 megahertz? The answer is in at least some segment of the band. And again, you go back here. What we're looking for is that little green area, and you'll see that every band has a little green area. CW only, which is Morse code. Well, CW only is a little dark red area. So 6 meters, 2 meters, 222. Those all have little sections. There's also a separate section of 219 to 220. This is truly memorization. You just have to remember it exists. A long time ago, the United Parcel Service came along and said, we want to create a radio-based service for scanning packages. They said, how about we trade 1 megahertz of our band to 2 megahertz of a ham band? And because there were very few people using it, the FCC said, okay. So they took 2 megahertz of our band and they gave us this disconnected 219 to 220. And you'll notice that it starts at technically 222, but we also have 219 to 220, but it can only be used for this one purpose, which is kind of a weird purpose. And again, that's just memorization. It's a very weird thing. Why should you never set your transmitter to be right at the edge of a band? Well, you don't know where you're going to be exactly. So the reason that I say that is because we have this frequency right here. Let's say we draw a frequency chart, and on the 20-meter band, we can go from 14,000 to 14,350. Where are we allowed as hams, if you have appropriate privileges, where does the FCC, we can tune our radio in there?
Anywhere.
Anywhere, literally anywhere. There are no other services that I am aware of where you can just tune your radio anywhere. Everything else is channelized. We can tune anywhere. There's only one caveat. What is the caveat? Our entire signal that we transmit has to be within those two goalposts. That's it. That's the only rule, other than, following the right modes and things like that. So if we transmit upper sideband, here's upper sideband. This is 3 kilohertz wide. We never want to tune above 14.347 because what will happen to our modulation sideband?
It'll be over the limit.
Which is why we have to understand what our signals look like. Again, we're not appliance operators. We're given pretty much free rein to do this kind of stuff. So we have to truly understand exactly what our signals look like and how they behave on the band. With great responsibility comes, or with great privilege comes great responsibility, or something like that. So if we tune too high, our frequency spectrum will look like this and will be outside the band, and that will actually be breaking the law. We don't want to do that. We could also be that even if we tune to the right frequency, what can happen is that our radio might not be accurately displaying the frequency properly, and we may actually be off by 1 kilohertz that way, in which case we will inadvertently be spilling outside the band. So that's why you don't ever want to get too close. Okay, and we're coming up on 2 o'clock. It's good because we're coming up on the end. Okay, we are not. What? Oh, how are we restricted in segments of bands? We are secondary. We are not always primary users. We have sharing agreements with the military and with other services. If we are not primary, we have to make sure that we are not interfering with anyone else. Above 30 megahertz, our peak envelope power is 1,500 watts with a few specific restrictions. On the HF bands, if you're in a technician segment, you can use 200 watts of output power. I don't even have a 200-watt output transmitter. For what license classes can you actually obtain from the FCC right now? They're called Technician, General, and Amateur Extra. No, I don't know why it's called Amateur Extra, and the others are called just Technician and General. You'd think it would be Amateur Technician, Amateur General. I don't know. That's always been that way. An FCC license is good for 10 years. They don't send out mail or paper anymore. If your license shows up in the FCC online ULS database, it is a valid license, and you can possess one license. You can't have more than one. It's assigned to you. If your license shows up in the database, you're valid. If you have a license, you can apply for a vanity call sign, which means you get to choose your own call. When you pass an exam, you get assigned a sequential call sign. You may love it, you may hate it. If you really hate it, you can pay the FCC another $35 and apply for a vanity call that you like better. Notice that we can actually choose from call signs that begin with W, N, K, or AA through AL. Those are the only prefixes that the United States has been assigned. All the other prefixes that you can think of are assigned to other countries in the world.
If you upgrade your license, do you get an entirely different call sign? Or
if you want, you can. You don't have to. You can keep the call sign you have if you like it.
Okay, thanks.
Yep. If your license expires, it stays in the database for 2 years. It is not active. You can't use it until it shows up as active, but it's not actually expunged from the database until 2 years has passed. A club, the definition of a club is 4 members. If the FCC can't reach you by email or snail mail, both of them, they can revoke your license. So keep your contact information active in the FCC database. What is considered part of the United States? Okay. If you are on a United States flagged ship in international waters, that is considered part of the United States. You might still have to check with the captain to make sure it's okay to transmit, but you can use your own call sign. Things that you're not allowed to say. George Carlin had something called 7 words you can't say on television, I believe. And those are still in force. You know, there are certain things that you really shouldn't say. The rule is basically you can't be indecent. And if it's something you wouldn't say to a 7-year-old, don't say it on the air. That's the easiest way to think about it. When are you allowed to transmit music? Typically not, unless it's incidental. And let's say you're providing communications at some kind of festival and there's somebody playing music in the background, probably okay. But we are not a broadcasting service. We don't broadcast. We definitely don't broadcast music unless you have a manned spacecraft, such as the International Space Station. We used to wake up the astronauts on the space shuttle using music that was rebroadcast by NASA Goddard and NASA Johnson Space Center, and it was okay to do it. They got authorization to do it. That's the only time we can transmit music. When can you obscure the meaning of a message? Only if you're controlling a space station or remote control craft, because we don't want it to be crashed into the ground. Who are we allowed to talk to? Unless the ITU, which is an arm of the United Nations, International Telecommunications Union, unless a country has said, you're not allowed to talk to our people, we don't want our guys talking to their guys, you're allowed to talk to anybody you hear on the air who is a ham.
So is North Korea?
They are okay. If they ever gave out a ham license, we could talk to them. We're waiting for the day. There's a lot of people who are missing one country. Guess what that country is? In which of the following circumstances can the control operator of a station get compensation? Okay. In other words, when can you get paid? If you're a classroom instructor, like a teacher in an educational institution, you can use ham radio for instruction of science classes and things like that and still get your salary.
That's wrong.
If you're not selling equipment on a regular basis and it has something to do with amateur radio, you can announce it for sale. We have swap nets for that. Broadcasting is transmissions intended for the general public. We typically don't do that, like ever. So we may do one-way transmissions for the amateur radio community. There's something called Amateur Radio Newsline. It's meant to be sent out as a one-way communication to hams. It's like a bulletin. We can do that because it's meant for what community, which is us. When are we allowed to transmit information in support of broadcasters? News gathering, stuff like that. There's that word again. If you ever see immediate safety of human life or protection of property, basically, if you're the only way that a TV station, which lost their link, can get the information out that says that there's a dam about to break and it's going to flood the town, you can go ahead and do it. Okay, so who can you talk to? What can you say? Communications incidental to the purposes of the amateur service and remarks of a personal character. I used to laugh at this because most people that I would hear on the air who are above a certain age would talk about all the doctor's appointments they had to go to. And, oh, my sciatica. Well, you know what? I've got sciatica. I'm 55 years old, turning 56, and I understand now. It took 40 years to get here, but I understand what they were talking about that I used to laugh at because I do the same thing. When may an amateur station transmit without a control operator? Never. Okay, so There's a concept that we're getting to, which is control operator and control type and station licensees and stuff like that. So your license actually has two pieces to it. There's a station license and an operator license. An operator license permits you to operate an amateur station. A station licensee licenses the physical equipment. For instance, this right here, this handheld in my hand, this is an amateur station. It is equipment used to send out signals, send out radio waves. This is an amateur station. I am holding the station in my hand. This is the control point. This is local control because I have my finger on the button. I'm in control of the station and I am the control operator. I am using it because I am licensed to operate an amateur station by my call sign, by my license. Right? I'm also the station licensee. I am licensed to have that equipment. That's kind of two separate things. So who does the FCC presume to be the control operator unless there's other documentation? That would be the licensee of the station. Who designates the control operator? The station licensee. I could have somebody come and visit my station and say, okay, well, you've got your license. You can use your call sign. Go ahead. If something goes wrong, it's both of our faults because it's my equipment and it's their license for operating. The control operator of the originating station is responsible if a repeater, for instance, sends out a violation of FCC rules, like somebody cursing on the air. The repeater owner is ultimately not responsible for that because it's automatic. What determines the transmitting frequency privileges of an amateur station? Again, everybody, what is a station? What defines a station?
The equipment.
A pile of equipment. A pile of equipment defines a station. It could also just be a handheld radio. So the transmitting frequency privileges, what if I own the station and somebody with a technician license walks in? Whose privileges does that station operate with?
Depends who's operating.
That's right.
The technician is operating, it's only the technician license.
Okay, how about this one? I have a club station, W0 AXE, which is the South Eugene High School Radio Club at South Eugene High School. W0 AXE. It is a station license for a club. It has no license associated with it as far as a control operator. Can somebody just walk in and use it without a license?
No.
No. The station license defines the club's call sign, and that's all. It has no privileges at all. However, if a technician operator walks in, they can operate where? On a technician class area of the band. If an extra class operator walks in, they assume the control operator responsibilities, and it can operate with extra class privileges. There's also something called a trustee. The trustee is ultimately responsible for a club station. Most trustees are extra class operators because then it doesn't seem weird at all if that club is operating with extra class privileges. That's why most trustees are extras. Okay, let's see. Under normal circumstances, can a technician class licensee be the control operator of a station operating as an extra class station? The answer is no.
Okay.
Great. Okay, who can be the control? Go ahead.
If you have an extra class person there, a technician can operate the radio with the extra class person there. They just use their call sign, correct?
If you use the club call, it depends. Literally, you'll turn and say, okay, I'm the control operator now. And while you're there as the control operator, you are responsible for what comes out of that other person's mouth because you're the control operator.
Right.
Even if they have a technician class license or even no license, if we're operating under a third-party agreement, which that does exist, You're ultimately responsible for whatever comes out of their mouth.
Right, but they can use the radio under your control and supervision, and you can allow them to operate the equipment.
What happens if you walk out to use the bathroom?
Then they have to stop.
That's right.
Okay, I just was trying to remember that. Thank you.
Yep, excellent. Okay, so who can be the control operator of a signal going through a satellite or space station? If you're allowed to transmit on the uplink and it gets moved somewhere where you don't have privileges, someone might think it's odd that your signal showed up there. But since you didn't move it there, you transmitted legally, then it's perfectly fine. Okay, control point. Control point is where a station is being controlled from. If you're operating over the internet, that is known as remote control. The requirement is that you must be physically at the controls and a station cannot be unmanned and operating, which means if I'm operating over the internet and I lose my internet link, what has to happen to the station? What do you think?
It has to fail off.
It has to fail in the off position. Exactly. It has to shut off because I lost my link and I'm no longer the control operator. It has no operator. It has to turn off. Okay. How often do you transmit a call sign? At least every 10 minutes and at the end. Oddly, you don't have to give your call sign at the beginning. We have one guy in our club who loves doing this. And it's really it's perfectly legal.
I have a question on that. Why do they require the every 10 minutes? Station ID.
That's just something that has always been. That's in Canada, it's every half hour. FCC rules say every 10 minutes.
Because a lot of stations, commercial stuff, requires call sign
once an hour.
Every hour. Right?
That's right. This is every 10 minutes. That's how the rules were made. Like I said, I have a Canadian license. I had to remember that in Canada, it's every 30 minutes, just because that's what the rules say.
I just wondered if there was a reasoning behind it.
Not that I've ever been aware of.
Okay.
Okay. When can you transmit without identifying? Only if you're sending signals to a model craft. If you have a Futaba controller or something and you're controlling a helicopter, perfectly legal. You can transmit with 1 watt of RF energy, 1 watt of power. Your name, your address, and your call sign have to be on the transmitter. Those are the special rules for that. When operating in a phone subband, again, phone is voice. You have to identify in English. You can have your whole conversation in any other language you want, but when you give your call sign, it has to be in English. When I was in Chile, I had conversations in English, but I had to identify en español because that was the rules of operating in that country. To transmit phone signals, when transmitting phone signals, you have to identify them using your phone signals, which is your spoken call sign, or you can have Morse code in the background. A lot of repeaters have Morse code in the background because it kind of goes over top what you're saying. It doesn't distract from the conversation. When using phonetics, we use phonetics because phonetics eliminate ambiguity, especially if you're spelling a name that is complex or there are multiple different ways to spell it. We can do something called tactical call signs. A tactical call sign is a non-ham radio call sign that identifies where you are, such as race headquarters or aid station 3. This is something that we do a lot during emergency communications, but it's not a call sign. You still have to follow the FCC rules, which means every 10 minutes and at the end, you have to identify using an actual call sign.
On phonetics, is there a specific ham phonetic?
No.
Okay.
We typically use the ITU phonetics, but no, I mean, you don't have to use phonetics at all.
So I
it just really helps.
Use the military one that I've known all my life.
Yeah, exactly.
Okay.
Self-assigned indicators, either the word slash, stroke, or slant are valid. When they say self-assigned, if we're operating in a different part of the country, for instance, if I'm a W7 and I'm operating in Maryland, I would say /W3 so people would know where I was, or just /3. Okay, third-party communications. If you have somebody who's unlicensed come to your station and you want to get that person in touch with somebody else on the other end who is either licensed or not, that becomes third-party communications where they are. We just did this last night. Emma, you were just on the air. Did you know that you were doing third-party communications?
No, but I'm really, really glad I didn't curse now.
That's right. So third-party communications, basically having a third party operating under your license. On the other end, it could be another third party who was operating. So that could be spoken by them themselves, or it could be something that they wrote for you that you passed along. That's still third party communications. We don't have third party agreements with every country in the world, believe it or not. There's a list of them available at the FCC website, and another one at the ARRL website. When allowing a non-licensed person to speak to another station, we have to have that third-party agreement. And finally, if the FCC comes knocking on your door at 3 a.m. and says, "Look, we really need to see your equipment," you have a license. They granted you the license. You have to open the door and let them see it. I don't know anyone personally that this has ever happened to. You'd have to do something really bad for this to happen. And that's the whole thing. And we're only 15 minutes late. We're only 15 minutes late. And tomorrow I get to start the general class. Scott, you know somebody that happened to?
Yeah, he told me there was somebody in the neighborhood that was broadcasting illegally, or not broadcasting, they were transmitting illegally on. I think it was a C-Beer that was, I don't know how he got on 10 meters or whatever it was, but they thought it was him because they saw the antenna and they knocked on his door at some weird hour of the night and they insisted. And in fact, they almost threatened this guy that they would arrest him if he didn't let them in. They had to see his equipment right then and there. So
Okay.
yeah, I did know somebody that was some years ago, but it did happen.
Wow. Okay. Well,
Yeah.
the other interesting thing about the FCC is they have incredible powers of triangulation. The FCC van is a real thing. They have some really, really awesome tools that they can use to find offending stations. The other thing they can do is, you would not think so, but did you know that this radio, which is a Yaesu FT60, of which there are probably, 100,000 copies that have been made in the world, maybe more, is unique from every other one? Think about that for a minute. Why is that unique from every other one?
For identification.
Yeah, well, I mean, there's nothing specific. It has a serial number, but it's unique from every other one. Every single radio has a unique footprint. When you key it and it shifts from receive to transmit, it actually has a key on, like, fingerprint.
Probably like a MAC address, so it can be identified.
No, it's not like that. This is actually when the system switches from receive to transmit, it makes, because of the specific components that have been used, the capacitors, inductors, timing, everything, makes it have a unique address that the FCC can actually match transmitter fingerprints with.
Yeah.
Isn't that cool?
No.
Is
Yeah, well,
is that only on the Asus, or is it on
no,
the
that's on
Baytex as
every
well?
radio. Every radio, when it switches from receive to transmit, has a kind of like a unique fingerprint.
Oh.
Because everything doesn't have the same soldering and same
What do they
everything
do?
else, right?
That's
Basically.
And to say too much solder.
How do they see it, Scott? How do they determine that fingerprint?
Well, if they know what the signal looks like, they can watch the signal as it goes from receive to transmit, and if they get a spectral analysis of it and analysis over time, and they look at it fast enough, they can actually see the rise time and everything, and it's typically repeatable within a transmitter, and they can tell multiple transmitters apart.
Wow, forensic Forensic spectral analysis.
Yep.
Interesting.
Scott, I have a
Yes.
question.
Big Brother's always watching.
Well, I mean, you got to do something really bad, you know.
You're not gonna just pick any.
No, but that does help. For instance, if it's more common that like somebody is going to have a transmitter that's putting out a spur, which is a spurious emission, on some frequency that's interfering with something else, either public service or air traffic control. And if that's happening, they're going to find it. Even, you know, and more than likely you didn't do it on purpose, but you know, if they say, okay, you got to stop using this thing like right now, then you better stop using that thing right now.
God, I have a question.
Uh-huh.
So I am living now in a different region than the one where I got my license. Should I have been identifying myself with a stroke and the new region?
Where do you live?
Well, I got my license in Utah, so I was 7,
Right.
and I'm living now in Georgia, so it's 3, I think, or
No,
4.
it's 4. Georgia's 4.
So have I been violating that rule all along?
No, there is
Just
no
don't know
rule.
this.
But you're in 4, so you'd say /4, or you could just use your old your call sign as it is. And
So that was my question. Am I required to say
no
stroke something?
Unless you're in Canada. If you're in Canada, you have to do it because you're in a different country, or in a different country somewhere else in the world, which you have to identify. But in the United States, like there's not even a requirement. It used to be that if you moved from one part of the country to another, you had to get a new call sign based on that region. And many years ago, that went away.
So that would still not be considered something like best practice to get a call sign with the correct where you live.
A lot of it depends. I mean, in Oregon here we have N7JI.
Yeah, we have lots of different call areas.
Yeah, and you know, like if she's on a repeater here, then we know who K9JOY is. You know, because we hear her all the time. The question is whether or not that gets confusing. Like if you're in a contest or something, and let's say somebody answers K9JOY, okay, well, let's say they think, okay, well, they're kind of marginal, you know, signal strength wise. I got to turn the antenna. Well, where are you going to turn the antenna to? You're going to turn it to 9-land. 9-land is Wisconsin, Illinois, Indiana, right? But it turns out that unless she said K9JOY/7, there's no identification that she's in Oregon, right? So, and you end up turning the antenna the wrong way, which is why people will do that if there's some reason to think that they're going to be aiming the antenna the wrong direction or something like that. Which is also why a lot of people will just go ahead and get a call sign that identifies where they physically are.
Yeah, that makes sense. It sounds like a good practice.
I'm sorry. Clarification.
Sorry.
Who goes first? Linda.
A quick question. My uncle is very, very old. He got his call sign in 1946, and he wants to give me his call sign.
Okay.
See any problems with that, or?
You know, does he want to do it like immediately?
Right before he passes, I think.
Yeah. Okay. So basically, I don't know if you can voluntarily, give up a call sign. I know you can probably have the FCC cancel it, in which case it goes into the pool after 2 years. And during that time, anybody else can request it who is a family member.
Okay.
So he can't give it to you, but he can give it up and you can request it and say, I'm his granddaughter.
Okay.
So you should be able to do that. But I don't know many people who've voluntarily given up a call sign unless they go pick another one.
Yeah, but is there any advantage to me? Do I get like instant street cred because my call sign is so old?
What's the call sign?
I don't know what it is right now.
What's his name?
Oh wait, Linda. I just want to give this guy. Yeah, I know a lot of people who've done that, and And yeah, I mean, it's like if you're a tech and you have like a W7A, I mean, or whatever it is, it's like usually a 5 character call sign or something like that. That doesn't sound like you got it that was recently issued. Yeah, but there's a lot of people who do that. You know, in my family, it's been done, and you know, I know tons of people who have done that. And there's, I mean, it's kind of cool. It's just a thing that's for you personally is a nice thing that you carry on. You know, so
Linda,
you know,
what's his name?
James Flanders.
Let's see how many James Flanders there are. There are 3 of them. Londonderry, New Hampshire, Plano, Texas, or Bozeman, Vermont.
Plano.
W0OOG.
Oh, that's a cool one.
Woog.
Yeah.
W0OOG. Okay, so let's see here. Is that him?
Yep, that's him.
There you go.
Oh, seems like he's a pretty active guy.
Very. His whole backyard is all antennas.
Yeah.
Probably the best thing to do is wait, you know. I mean, unless I don't think he wants to give up his call sign at this time.
No.
Well, he just went into a home.
Oh, well, I mean, it's up. I guess you guys can check it out with the FCC because I don't know.
He just doesn't have anybody else in the family interested, and he's really protective of it, and he wants it to carry on.
Yeah, that's understandable. Yeah, check with the FCC and see what their policy is on that.
Okay, thank you.
We can help find out for you.
All right, now, who had another question? Who had another question? Somebody raised their hand.
I have one. Well, okay. Is Morse code still common out there, and how do people on the receiving end know what they were transmitting?
Well, I mean, tons of us still do it every day.
It's very popular.
Huh. Okay.
More popular than you believe, right, Scott? I mean, you go on any contest, and you look at the CW portion of any band, and they're
wall to wall.
There's more. I think there are more CW operators that get involved in contesting than even sideband operators.
I think that's largely true. I mean, it's everywhere. And
you can learn CW. I mean, there's a couple of ways you can do it online, and you can teach yourself, right, Scott?
It has, and the thing is, it hasn't been required since 1994.
Is it that long? I thought it was 2003 they dropped it.
Was it 2003?
I think that's what I remember. My father.
I mean, it's been 20 plus years since it's been required. Yet, you get a lot of people. I mean, I'm a member of multiple different CW clubs, and there are tons of people who are in all these classes, and tons of newbies who are learning Morse code, because you find, okay, number one, it doesn't require a computer. You don't need anything to decode it other than your head. Number two, it's very, very narrow band, which means that it has, very high power spectral density. Number three, you can get away because of that with running a 5-watt transmitter in a lot of cases, which makes you exceedingly portable. So you can, essentially the rule of thumb is that 5 watts Morse code is equivalent to 100 watts voice. So, you look at that, and I mean, okay, I've made contacts using Morse code from inside a hotel room at 5 watts in Austria, and I work something like 21 countries using a loop antenna inside a hotel room. I mean, countries in Europe are kind of like states here. They're, really nearby, but still. It's just makes it really, really easy. Mentioned transmitting photos. Okay, so that'd be slow scan. I've only done slow scan once with somebody else. Scott, you ever done slow scan?
I have not personally, but there's a slow scan net on the WE780 repeater every Wednesday night. And those guys, they transmit pictures back and forth to each other. You can go on the international, if you on certain designated times, the International Space Station will broadcast photos, and you can use the slow scan TV software on their downlink frequency to generate their pictures.
And you don't have to do anything special. You can actually just hold your radio up next to your phone, running slow scan receiver, and it'll actually pop up the photo on your phone after about 30 seconds. Hey, Brett, your hand's up. You must be getting tired.
Yeah, thanks. I had a question about the identification for a call sign in a different jurisdiction from the number designating wherever you're from. So I've got a California call sign. I'm often up here in Eugene. I've never checked in on any local nets or anything like that.
Well, you should.
I know, I'm remiss, but I was kind of curious, where would I say KM6/7 or KM6QIK/7? I guess
well, I mean, you could just do KM6QIK.
Okay.
I mean, it's, I mean, we're not going to recognize your call.
Right, but I mean, not being confusing about possibly being a.
Nah. Okay. I mean, on 2 meters, we know you're not going to get in from California.
Okay. Thanks.
Other questions, thoughts, comments? You guys want to know something about going and taking an exam, scheduling one? I mean, because that's, getting prepared. This was a start, but you still have to take a test. You still got to go schedule something and go do it, which means you got to prepare. So, all right, who wants to start? I mean, okay. So I personally am a big fan of the study apps. I like one in particular called Ham Radio Exam Online, which is free. And it works really well. You study one section at a time and just drill on one section at a time over and over and over and over and over till you get 100%, and you go to the next one. And, as far as going and taking a test, if you're doing entire exams and you're getting 85% or higher every single time, you're going to pass. If you want to eliminate the stress completely, the whole question pool is available. I mean, we can take a look at the entire question pool with all the answers. The book that I sent you is basically built around the question pool, the whole thing. So if you study that and study all the questions and study all the answers, you're going to pass. If you've prepared and you're getting 85% or higher, you're going to pass.
Scott, I might just be looking wrong, but I've looked at the two in-person links that you sent.
Mm-hmm.
Do people just not do in-person exams anymore? Because the closest one is like February.
No, there might. I would think the Valley Club is doing one in January.
I'm just asking. I thought you were going to give the test here.
No, we're not doing the test here.
Oh.
But if you're looking to take a test, like you want to take one tomorrow or this afternoon?
No, I don't. I'm not really, but
are you sure? Because you can. I mean, I'm not going to give it, but if you go here, Ham Study. Okay, so first of all, Ham Study is a really good place to find exams, but not everybody will list their exams on Ham Study, for one thing. So right? So for instance, there's one in Astoria. You can probably do a search of some kind. I don't know if the Valley Club is going to list it here, but if you're looking to do one in person, let's see if they got one scheduled.
Well, okay. Thank you very much. I appreciate your answer.
Yeah, I mean, there's a lot of options.
We're giving one at the beginning of February.
Right, but then you got to wait till February. So, you know,
we're going to try to do it sooner, but I don't know.
let's see, entry level license, class, et cetera, et cetera. I want to look at the calendar. And there's, let's see, halftime, halftime, halftime. Exam session, January the 13th. Oh, wait, that's December. I spoke too soon. Exam session, January 10th in Eugene. So Ezra, there's your target, Ezra.
Cool. Is that like a sign up on the website or?
See, let's just call Brad.
Oh, okay.
Call or email Brad. He'll
Okay.
get you on the list. And you know, the cool thing is if you go and you take a test and you feel like you're doing well and you want to start studying for the general and get to the point where you're doing okay on the general, it does not cost any extra to take the second exam if you pass the first one.
Yeah. I
And
mean,
that's why, you know,
my
that's
dad
why
was going to do that, and then he was like, "Oh wait, the technician's kind of hard."
it's not that hard.
Yeah, I don't know
It's,
what he was thinking.
yeah, it's not that hard. And in fact, for people who do well on the tech, I strongly recommend trying out the general if you're doing well, because there's about 50% overlap of the material. And actually, for anyone who didn't read it, our general class starts tomorrow, 9 to 1. Gonna be fun.
Yeah, he.
Yay! Yeah.
Thank you. Thank you.
Any other questions? It's a good time to ask.
So, Scott, I just barely hung on some of the radio stuff you were talking about, and I couldn't keep up with all the terms. Am I just going to die in the general
No.
class the
Why
next
would you
2
think
days?
that? Why would you think that? When you say, well, which stuff are you talking about? What do you
Well,
feel
I
you need
don't
to be
even know
stronger
the
on?
difference between an ohm and an amp and that stuff is all new to me.
Well, let's do that right now. What's an ohm?
I don't
What
know.
is what it? I'll bet you do.
I
It's a
don't know.
unit.
It's got something to do with power. I don't
No,
know.
an ohm is a unit of resistance. This is memorization. This is
Right. I
just
just need to sit with the book and let it sink in.
no. What you need to do is solve problems. EMF. A watt is power. So like, I don't mind. I'll cook one up right now. Okay, here we go.
And I know that some people kind of say that this is wrong, but it's helped me to think of volts as like how hard it's pushing
That's
through
exactly
the
right.
wire.
Actually, who said that was wrong? I'm gonna go beat him up.
Garden hose analogy.
Yeah, it is. Okay, so let's say that E is 20 volts DC and R is, okay, what are my units going to be for resistance?
Ohms.
Yeah, okay, so they're going to, resistance is 10 ohms. Okay. Current, we don't know the current. Okay. Give me the circle to figure this out. What's Ohm's law?
E over IR.
E I R. That's our circle. You just have to be able to draw that and know that E, what is E?
Voltage.
Volts. And I?
Amperage.
Amps. And R?
Resistance.
Which is ohms. All right, so which one don't you know?
Amps.
Amps. Okay. So we have I is equal to E over R.
So it's 2.
Yep, because it's 20 divided by 10 is 2 amps. Okay. That's our current. Okay. So now what's our power?
PIE.
Yep.
Yeah, but I still don't know what amps is.
Amps?
I mean, I get the math, but what is it?
Amps?
Yeah.
Amps is current, right?
Well, okay. Is that like the electrical amount of electricity that you have that you're forcing through?
That is the number of it's a measure of the number of electrons that are flowing over a point.
Think of water
this
flow.
point. Yeah, it's the current. It's like the current in a stream.
Okay.
The bigger the current, the more stuff is flowing through the stream.
How much water is coming out of the hose?
Right.
The pressure coming out of the tap is the voltage.
Yep.
Resistance is
how narrow the stream is.
Right. If you're squeezing off the hose so the water can't pass, that's resistance or ohms.
All right. So your current is 2 amps. Now, what we want to know is essentially how much work is being done per unit of time by this circuit. How hard is it having to work to do all this?
Well, that must be the voltage, right?
No, voltage is how much it's pushing. What's causing the push? What is this device right here?
Where?
What is that device right there?
Battery or power?
That's a battery.
DC.
The battery is providing the push. That push is measured in volts. And that's why we call it electromotive force, which is why it's the letter E. Because electro is electron, motive, movement. So it's the force that is moving electrons. The higher the voltage, the harder the push. Okay, so now we have to figure out how hard it's being asked to work. And that is the other part of Ohm's law. And what's the other part of Ohm's law?
The other circle with the different letters.
That's correct. Which is?
I don't know. I don't remember.
E over IE.
Well, it looks like a pi.
Oh yeah,
This is
there's
the
a
easy
PIE.
one. This is the easy one because it spells the letter pi.
Right.
Okay, so what's P?
Well,
power?
That's power, yep. And I again?
Is ohms or resistance?
I is current.
I is current. I is current. Yeah, I thought A was current.
No, it's measured in amps, which is A. And E is our voltage, measured in volts. And power is measured in watts.
Oh, watts.
Okay, so if we know that our battery is delivering how much voltage?
20 volts.
20 volts. Okay, and how much current is it delivering?
No, we don't know that.
Yeah, you do know that. It's 2 amps.
Oh, because we figured out before?
Yep.
Yes.
And P is equal to I times E is equal to 2 times 20.
40.
40 watts. So let's say that you were to replace this battery with, I don't like that color for this. There we go. With a hand-operated cranked dynamo. And here's you turning this crank.
Oh, now you're just being mean.
No, this is us having to turn this crank over and over and over, round and round and round. All right, to get it to run. The battery was putting how much power out?
40 watts.
Okay. How much power would I have to be putting out to do the same thing?
40 watts.
40 watts. It doesn't matter where the power is coming from. Power is power. Wattage is wattage. If I have a battery that is generating that voltage, I could be generating it like this. And using this to turn a generator. I could do that. I could be using this as my power source. And I could be using this for a resistor. And this would have to be generating to do the same thing, 40 watts. Doesn't matter what the source is. It's a battery, it's a water wheel. I didn't draw that water wheel completely well, but if I do this like a paddle wheel, a battery is just a chemical source of energy. It could be anything. It could be a guy on a bicycle, right? Power is energy per unit time. That's all power is. It's a rate of energy delivery. And it doesn't matter where that energy comes from. Energy is neither created nor destroyed. It just changes form. It could be chemical. It could be, like it could be heat. So I might have, let's say, so in between, let's say I have a flame over here. And on this other side, I have a block of ice. And in between, I have a device, which is called a Peltier junction. When one side is hot and the other side is cold, it generates electrical power. This actually works in the other direction. I'll bet you've even seen one. If you put electricity in, it generates heat and cold at the same time. Does anybody have an RV refrigerator? One of those little portable 12-volt coolers? Ever seen one of those?
In a boat, I guess.
Yeah. Well, you plug it into 12 volts and it generates heat on one side and makes cold on the other. If I have 40 watts going in of electricity, I will get 40 watts in theory of heating or cooling on the other side. That's the great thing about power and energy. Energy calculations make things really easy because you don't end up destroying anything. It just moves around.
All right, well, I'll try the general class.
Okay, so what's the unit? What's a unit of current?
Amps.
Yeah, okay. And
I
what
looked
is
at my notes.
That's fine. And how do we and what is current a measure of?
Number of electrons flowing through.
Yeah. Flowing across a certain point. And what's voltage? What units do we use for volts?
Volts.
Okay. Or for voltage, yeah. And what's voltage a measure of?
That's the garden hose, how fast it's going.
Well, it's how hard it's pushing.
How hard it's pushing.
Right. And what's resistance? What are the units of resistance?
Well, that's what's holding it back.
Right. And what are the units?
Ohms.
Yep. And who's it named after?
Mr. Ohm.
Mr. Ohm. I don't think he was Dr. Ohm.
Georg Ohm.
Yep.
Lived in the 1830s. I think he did the experiments in the
There he is. Georg Simon Ohm. And who's the Volt named after?
Volta.
Alessandro Volta.
That's quite a
Yep.
name.
Yep. And how about Ampere?
Sounds French.
Yep. I believe it's Jean-Louis, what is it? Jean-Baptiste Louis Ampere or something? Let's see what his real name was. Come on. Oh, Andre Marie Ampere. And how about the Farad?
Faraday.
Michael Faraday. And the Henry for let's see, Henry inductance. The Henry was named after Joseph Henry. So if you did all this work way back then, you got units named after you.
You'll notice all the fundamental aspects of electricity were discovered in the late 18th century and the 19th century.
Yep. Oh, look, there's.
We know all this stuff for many, many
years. Yeah. Look who that is. It's Heinrich Hertz.
Heinrich.
Okay, I want to mention one thing about Heinrich Hertz. This is why it's interesting where we ended up today. Here we go. I do not think that the radio waves I have discovered will have any practical application. Just remember that.
Yeah, we remember his name.
Yep. But that's what he said. I do